Hello, everyone. My name is Yankee Hong. I am a session chair of EPMM-4. First speaker is there. Who is the first speaker? Dr. Penman. First author name is the Penman. Is he here? Once again, hello everyone. Welcome to EMPP-4 session. My name is Yankee Hong from Electrical and Computer Engineering at the University of Alabama. I'm calling first speaker of a first paper. Penman. Second paper speaker here. Abstract number 490. Third paper is the abstract number 184. Can you please raise your hand? First paper, abstract number 346. 346. First author, last name is Penman.
Okay, I'm here.
Second paper, abstract number 490. Mansramel is not here. Third paper, abstract number 184.
Excuse me, Professor. We have some recorded videos, and maybe the speakers are not here. We can play their videos.
Yeah, we will begin this session at 3:20. Just 1 minute left. I'm checking speakers.
Okay.
Each paper will have only 10 minutes. So please submit 10-minute time frame. Otherwise, we will have trouble following speaker's schedule. Please submit time limit, which is the 10 minutes. Once again, welcome to session EPMM-4. My name is Yankee Hong from University of Alabama. Okay, now 3:20. First paper will be presented Animesh Jha. Last name is Jha. Jha here. First paper, abstract number 346. Last name of Penman, or last author Jha. If no one presenting first paper, we have to wait until 3:30 for second paper presentation.
Hi, Professor Hong. The first presenter has provided a record video. Shall we play it now?
Oh, They left you a recorded presentation?
Yeah, they have
Okay.
provided us
All right.
with a video.
Then we have to wait until 3:30 for second presentation. Thank you.
Shall we play the first video?
I don't know how to replay the recorded presentation.
I can play the video.
Can you share with us?
Yeah, I will share.
Good morning, my name is Animesh Jha. I'm giving this presentation on behalf of my colleagues, and the topic is the spectroscopic and magneto-optical properties of terbium and manganese dope CDS quantum dots in silicate glass for Faraday rotation. This is a collaboration between the universities of Leeds and Pune and CMET Lab in Pune, which was funded by the Royal Society. Let me introduce the importance of Faraday rotation in controlling signal processing. As the light propagates in a medium, the temperature, pressure, stress, and refractive index of a solid state media can influence the polarization state of the propagating photons. That means we would expect a dispersion of polarization when light is propagating in the medium. This is very important, particularly when you're thinking about coherent signal processing. So for controlling the polarization state, we can utilize Faraday rotation as a technique for correcting the polarization distribution, and this way we can produce coherent signal all the time, provided the magnetic field required is small. And you can see from the equation that Faraday rotation theta f equal to Faraday constant times the field applied, magnetic field B, and length of the medium. Longer the length of the medium, the larger is the Faraday rotation. The next equation defines how Faraday rotation is dependent on the two refractive indices of ordinary and extraordinary waves. Omega is the frequency and c is the velocity of light. And we can then calculate the Faraday rotation from this the energy shifts, splitting of the energy states delta E naught, which is given in the equation 3. By controlling the heat treatment, we can control the quantum dot size distribution, which we can also characterize by UV visible near-infrared spectroscopy and photoluminescence characterization. In this slide, we can see the data for CDS glass, CDS and MNS doped silicate glass, and terbium doped silicate glasses. So you can see very clearly the band gap is dependent on the heat treatment condition, and from that band gap, using Bruce model, we can calculate the size distribution of quantum dot, and that gives us average size, and the same technique was utilized for terbium doped CDS glass. As mentioned before, we calculated the quantum dot size distribution using X-ray powder diffraction technique for both types of quantum dot containing glass, CDS glasses, and terbium doped CDS glasses. We also utilize TEM techniques where you can see the quantum dots, average size of quantum dot is well below 5 nanometer. And we can clearly see the lattice fringes within the quantum dots, which we analyzed also to verify the presence of CDS. In this slide, you can see how we have compared and analyzed the size distribution of quantum dots. You can see very clearly the lattice fringes. So we analyzed the particle size distribution using the TEM technique as a function of heat treatment and compared this data with the size distribution calculated from the band gap and X-ray diffraction technique. We also then concluded from that quantum dot nucleation of CDS inside the glass is occurring as a result of the supersaturation condition, arising from the immiscibility of the CDS phase in the silicate glass. Nucleation may be occurring during quenching, followed by the growth of CDS when heat treated. In this slide, we see how the UV visible spectra of CDS containing and terbium dope CDS containing quantum dot glass are changing, and it's becoming very large, particularly in terbium dope CDS glass, which contain 2% of terbium oxide. We can also see how the band gap is shifting in the transmission spectrum. Detailed analysis of Bruce model. This is the Bruce model, which tells us how we calculate the delta, the energy gap as a result of quantum dot, which is basically the energy of the bulk band gap energy of the bulk material plus the other term, which is basically coming from the effective masses of electrons and holes. And this is a very important formula which we use for calculating the band gap of various kinds of CDS and MN-doped CDS glass. We then went on to measure the Faraday constant by calculating the Faraday rotation as discussed before, and what we found that the observation of the highest value of the Faraday constant was 12 degrees per Tesla per centimeter square per centimeter in MN-doped CDS containing quantum dot glass, and this is resulting from the spin state resonance of the incident photon at around 405 nanometer, which is where the band gap of the CDS glass usually is. The spin resonance condition weakens as the wavelength increases. As we are moving away from the band gap of semiconductor, the spin resonance basically starts weakening, and as a result the Faraday constant also starts decreasing. The magnitude of Faraday constant also decreases with the increasing size of the quantum dot because the band gap shifts to longer wavelength, which is why the measured values of Faraday constant show strong dependence on the annealing temperature. This is quite important because by controlling the annealing, we can control the particle size and also the light scattering. And this is summarized here in the graphs C, D, and E and F. We also the mechanism
sorry
of
everyone,
is
because of
via
the
CDS excitation.
Because of the time limitation, we have to stop here. And the videos are available online.
Hello. Did you cut off recording presentation?
Yeah, because
Okay.
we have to
All
keep
right.
the schedule.
Let's move forward. Next to paper will be 490, abstract number 490. Speaker will be Fit Mueller. Fit Mueller. You will be the next speaker for abstract number 490. If not, Jin Fang, do you have a recorded slide?
Yes,
or
we have
second paper?
videos. We can share. Yes, we have.
Okay, can you turn on? Thank you.
The title of my talk is Physical Properties of Nanocrystalline TiO2 thin films prepared by thermal evaporation. This talk is being presented in the International Conference on Advances in Functional Materials 2021. Introduction. Metal oxides are crystalline solids that contain a metal cation and an oxide anion. They typically react with water to form bases or with acids to form salts. Here, M stands for the group 2 metal. Titanium dioxide has received much research attention because of its multiple applications, such as dye-sensitized solar cells, quantum dot sensitized solar cells, photocleavage of water, photocatalysis, and sensors. Titanium dioxide thin films have got special applications in protective anti-reflection coatings as well. It has got an excellent chemical stability over a wide pH range and in a large number of solvents. TiO2 exists in three major crystalline phases and an amorphous phase: anatase phase, rutile, and bruchite. The rutile phase is thermodynamically stable with direct band gap, while the anatase phase is metastable with indirect band gap. The anatase phase has higher photocatalytic activity, while the photocatalytic properties of bruchite phase have not been much studied until recently because pure bruchite phase without rutile or anatase phase is rather difficult to prepare. Both anatase and bruchite are metastable phases and under suitable conditions can be converted to rutile, which has comparatively lower photocatalytic activity. TiO2 thin films formed at low temperatures are usually amorphous. In the present work, nanocrystalline TiO2 thin films have been produced by thermal evaporation technique, and their structural as well as optical properties were studied. The main highlights of this work is preparation of TiO2 with thermal evaporation technique, which is challenging because of the very high sublimation point required to evaporate TiO2 powder, which is of the order of melting point of most of the commercially available boards and has found countably very few literature by this technique. Low thickness of the film was preferred for the possibility of obtaining nanostructured TiO2 films. The outline of my talk is synthesis of TiO2 thin films, structural analysis, morphological studies, optical characterization, PL studies, and will conclude the results. Synthesis of TiO2 thin films. TiO2 thin films were deposited by thermal evaporation technique at 400 degrees centigrade using thin high vac coating unit at around 10 power minus 5 bar base pressure. The substrate to source to substrate distance has been kept at approximately 14 centimeters. Here, the TiO2 powders with very fine uniform grains were used as the source material, which has 25 nanometer size. The structural analysis. Figure 1A shows the Xrd analysis of TiO2 thin film prepared at 400 degrees centigrade. Here it shows the signatures of the TiO2 thin film with two peaks only, whereas the source material, TiO2 powder, which has these mixed phases as well. The table 1 estimates, gives the estimation of interplanar distance, crystallite size, dislocation density, and microstrain. Morphological analysis. FESEM's image of TiO2 thin film prepared at 400 degrees centigrade is demonstrated here. It displays uniform distribution of identical grains throughout the image. The average grain size of the pseudo-spherical shaped particles is estimated as 22 plus or minus 2 nanometers. Optical analysis. The optical transmission shows significant transmission in the visible range and NIR region from 65 to 85%. The absence of oscillations observed in the spectrum is an indication that the film is quite thin. The refractive index N of the films are almost constant, showing high refractive index about 2.2 in the wavelength range 425 nanometers to 1600 nanometers as shown in the figure 3. This slide shows the Taux plot of TiO2 thin films grown at 400 degrees centigrade. Figure 3C shows the direct transition and D shows the indirect transition. The optical band gap for the direct transition is 3.39 electron volts, while that of indirect transition is 3.2 electron volts. The rotile phase of TiO2 is reported to have a direct band gap with e.g. 3 electron volts, while the anatase phase is reported with indirect band gap of e.g. 3.2 electron volts. The slight increase in the band gap value is attributed to the nanocrystalline growth of TiO2. Band gap values of bulk and nanomaterials can be related using the effective mass approximation and hyperbolic model by the formulae 1 and 2 given here. PL analysis, photoluminescence analysis. The first broad peak between 366 to 367 nanometers corresponds to the direct and indirect recombination between electrons in the conduction band and holes in the valence band. These values correspond to 3.31 and 3.39 electron volts. However, the relative intensities depend on the excitation intensity. The other prominent bands are marked in the diagram. Now I will conclude the results. Nanocrystalline TiO2 thin films were successfully grown by thermal evaporation on BSG glass substrates, borosilicate glass substrates. Xrd patterns revealed a mixture of anatase and rotile phases, and the origin of the mixed phase is identified as the source material itself. The SPSCM image of the TiO2 films exhibit high-quality nanocrystalline structure with uniformly distributed identical grains with 22 nanometers grain sizes. The film showed significant transmission in the entire spectrum, slowly increasing from the visible side to the NIR side from 45% to 85% of transmission. Thickness of the film was estimated as 92 nanometers. The refractive index of the sample displayed fast decrease in the UV region and a very slow decrease in the visible and IR region. Transmission data also confirmed the nanocrystalline growth of the film. PL spectra exhibited many luminescence peaks and also confirmed the band gap observations obtained from the transmission spectrum. I acknowledge.
Sorry, we have to stop here.
Thank you. Next paper will be abstract number 184 from Texas A&M University, Professor Lei Feng. Dr. Feng?
Here I am. Yes. Yes, sir.
Go ahead.
Can you, maybe I should go here. Okay, thank you for the introduction. I would like to talk a little bit about the organic electronic materials, probably mostly different from other talks in this session. I'm an associate professor at the chemistry department of Texas A&M University. My group focuses on functional organic materials. Especially, we're interested in coplanar rigid conjugate organic systems, so-called letter polymers, and also mostly conjugate pi systems. The reason why we're interested in rigidity of these organic molecules or macromolecules is because rigidity imparts a lot of interesting properties. If we think about the fundamental charge transfer through this molecule, it gives low reorganization energy. It also gives better molecular orbital or wave function delocalization. A rigid system typically has lower entropy. It also has engineering properties such as different entanglement compared to conventional polymers. Those will lead to a variety of different properties compared to conventional polymers. But today, I think I will focus on electronic, optical, and magnetic properties, which are the topic of this specific session. Let's see. Okay, so one of the molecules we were interested in is so-called quinacridone. Okay, so we made this compound so that this conventionally insoluble material now is soluble. It has a very interesting supramolecular or self-assembly property. It could dimerize or aggregate in solution through hydrogen bonding. Once that forms, it will be non-fluorescent and has a purple color, but you could dissociate this hydrogen bond and then lead to a orangish color while strongly fluorescence. So this way you can see that once you, for example, if you dilute the solution, you would turn on the fluorescence, or if you disrupt the hydrogen bond, it would turn on the fluorescence. And this kind of aggregation dissociation could also be triggered at using heat. So that at a high temperature, you'll see a increase of the fluorescence and change of the color. So utilizing this, we designed a type of hybrid material. So we blended this kind of supramolecular solution into a polymer matrix such as PDMS. Then we print it. It could be made into thin films, or we could print it onto fabrics. Here we show the change of the color by changing the temperature. There are also videos showing that if you put this on a hot plate, you're going to change the color as well. More strikingly, if you heat it up, you could see the turn on of the very bright yellow fluorescence. And because this is a non-covalent interaction, it could be recycled for many times without any degradation of the color or the fluorescence intensity. On to the next slide. We're also interested in synthesizing the letter polymers. I'm not going to go through the synthesis here, but we can make these fused ring macromolecules, which is unsurprisingly insoluble. But we could still solution process this by converting it into a soluble precursor through simple Bach protection. Now, this highly soluble material could be fully characterized and then used to cast thin films. And then once you cast the thin film, we could utilize the reversible reaction of Bach cleavage to regenerate the hydrogen bond and then get a highly resistant solvent and then chemical resistant thin film. So basically we could fabricate basically a thin film with very strong solvent resistance by using solution processing techniques. This allows us to explore some very interesting applications. For example, this actuator. So this is a collaborative work where we put this letter polymer on top of carbon nanotube sheets so that you could utilize a different expansion coefficient of the material versus carbon nanotube when you expose it to solvent vapor and then give you this actuating process. So I think this one shows that if you expose the film to external solvent, you can see a very big change of the shape due to the actuation process. And this could actually jump by itself due to the very strong force generated by this actuation. And very important aspect of this material is that its resistance against very harsh chemical attacks, unlike most other polymer-based actuators, which you cannot really use it against a strong solvent or strong acid or base. So move on. We also are interested in making polyaniline derivatives of letter polymers. We all know that polyaniline, a widely used conductive polymer, it can have different redox states, change color, and also be conductive when you acid dope it in an oxidized state. But polyaniline has a problem that if you fully protonate it and oxidize it, it becomes unstable. So it's very little is known about what's the intrinsic property of this fully oxidized and protonated state of polyaniline, so-called prenygranulin. And here we can make a letter type or few string analog of polyaniline, which will give us good stability and also allows us to study their electronic and magnetic properties. So this is the synthesis, which I would not go through. The first important thing is that once these are synthesized, it shows much better stability compared to conventional aniline, polyaniline derivatives because of the additional stranded bond locking the constitution so that it's entropically unfavorable to break the bonds. Very interestingly, that we could see now. Very interesting is that we now could fully oxidize the compound and fully protonate it. Now we could study prenygranulin salt without worrying about its decomposition. We could see it has very strong EPR effect, but more interestingly, it shows very strong, very nice polypermagnetism, indicating that there's metallic polaron or delocalized polaron in the solid state when you fully protonate it. And so this is indicating that prenygranulin should intrinsically be conductive, which is a little bit debatable before we publish this work. The polaron delocalization, we believe, is strongly correlated with the proton in this case. We also made a polymer version of this compound with molecular weight about 25 kilogram per mole. And this compound, again, shows very much better stability against acid and against the strong oxidative condition compared to conventional polyaniline. As you can see here, it could survive for over an hour at a positive voltage applied in highly acidic condition compared to conventional polyaniline. Again, this polymer shows very strong dominant polypermagnetism, and then it's also stronger susceptibility compared to the oligomers, indicating that again this is has delocalized the polaron among the polymer in the solid state by the polymer. So we demonstrate the stability by fabricating a electrochromic device. Here, we all know that polyaniline can change color if you impose redox chemistry on it, but it will soon quickly decay over time because the decomposition I showed before. But here, using the ladder type structure, we could maintain a very robust device over hundreds of cycles with a very wide redox potential window. So in this case, this switching process can be maintained in a robust manner because of the ladder type constitution that gives us this chemical stability. So I would like to conclude my talk with this chart I showed before, that the rigidity and the ladder type structure give us very unique electronic and magnetic properties and optical properties, and also stability, which allows us to explore their materials properties and applications. So I believe this will be a promising class of new materials we could explore in the future. Now, with that, I would like to thank my research group and funding agencies and the students and collaborators who have contributed to this work. And thank you very much.
Thank you, Professor Fang. Next paper will be abstract number 222 from Institute of Technology, Indonesia, and Synchrotron Light Research Institute from Thailand, and Tohoku University, Japan. Speaker will be Suwasumura. Dr. Suwasumura, please go ahead.
Yes, thank you very much. You saw the screen? The screen is okay?
Yes.
Okay.
Looks good.
Thank you very much, Mr. Chairman. Good morning, everybody. My name is Suwasumura from Institute of Technology 10 November, Surabaya, Indonesia. On behalf of our colleagues, we'll present our work concerns on the magnetic implications on KNN through multivariate doping. Materials possessing multi-properties such as ferroelectric, magnetic, has much fascinate for modern functional devices. For example, rare earth manganese oxides as a magneto-electric multifaric materials. It holds above room temperature, is important for both fundamentals and technology aspect. Another example is zinc cobalt oxide as a dilute magnetic semiconductor. Our concerns now on the KNN-based materials. The KNN materials has a great intentions because it has multi properties such as piezoelectric, dielectrics, and reactor. On the other hand, bismuth iron oxide has both ferroelectrics and ferromagnetics properties. Now, our objective in this work is to elucidate the bismuth iron oxide's impregnate magnetizations after it dissolves in the KNN matrix. To fulfill this objective, sample was prepared, started from powder synthesis up to centering. After that, the samples then characterized through Xrd for phase identifications and structure determinations, SANE for oxidation state determination of iron, and SQUID for magnetizations. Based on the Xrd analysis, the undoped KNN has an orthorhombic structure containing secondary phase. After bismuth iron oxide doping, then our KNN become tetragonal and no more secondary phase detected. That indicates that all dopants dissolves in the KNN matrix. Further analysis using refiled refinement confirmed that our samples has a tetragonal structure in which elongated for x equal and below 0.075 and compressed for x over and equal to 0.125. The science analysis of added key edge shows you the pre-edge, the edge, and the maximum absorptions of the crest. Further analysis by fitting using Gaussian functions reveals that the pre-edge splits into two peaks. Similarly, for the crest also splits into two peaks. In here, we observe the absorption peaks, which is formally no transition axis in this energy range. It's suspected that this comes from the mixing transition of 1s to 3d, 4s, and 4p. All energies fitted of our samples are higher than those of ferric oxides. For the analysis by taking the edge energy of iron foil, ferroxide, and ferric oxides and plot it against oxidation state, we can estimate the oxidation state of irons in our samples. It seems here that for low dopants present oxidation states higher than that of high dopants. Therefore, we conclude that our oxidation state of iron in samples are a mix of 3+ and 4+, and it will play a key role in the magnetic property. The magnetic measurements records magnetizations and applied magnetic fields, H, showing the linear MH curve for high part and non-linear for low parts. This means that there is a mixed ferroparamagnetic in the materials. When the linear part is eliminated, that reveals the ferromagnetic hysteresis curve. The low dopings showing soft typical magnetics, and for high doping showing the typical hard magnetics. It seems that is to relate the crystalline state, crystalline structure. This measurement shows that the substitution of PF dopants was able to impregnate the magnetic characteristics of the K9 system. This table shows you the numerical values of hysteresis variables. For the analysis by taking the saturations MS and plotting against the X, then we can construct the MS X relationship. The iron was thought has key roles on the magnetic impregnations. There are at least three aspects contribute to magnetizations. First, when the dopant ions are dilute, all unpaired electrons in the 3D subcells contributes to magnetizations. The second, when the dopant increase, that favorize the possibility of ions in PO sides change interacts to enhance magnetizations through good enough Kanamori rules double exchange, iron 4 or iron 3. In here, the super exchange iron 4 or iron 4 and iron 3 or iron 3 not contribute to magnetizations. The third, the interactions between the iron 4 plus and oxide vacancy assisted the production of magnetic polarons producing unpaired electron and hence the magnetizations. These three aspects compete each other, resulting curve flow of magnetic saturations against doping percentage, in which increase in the low dopants and decrease for high dopants. And now the conclusions of our work. Magnetic reactions in K9 occur together with multivariate dopants dissolve in the K9 matrix. Iron holds oxygen state 3 plus and 4 plus and has key roles on magnetizations. There are at least three aspects intervenes to the magnetization and compete each other to render magnetizations: unpaired electron in 3D subcells, double exchange of ferromagnetic ordering, iron 4 to iron 3, and bound magnetic polarons due to oxide vacancy. And finally, the magnetization increase at low doping and decline for high doping. For your information, detailed analysis for X0 to 0.075 has been published recently. You can refer to this DOI. Thank you very much.
Thank you, Dr. Suasmoro. Next paper will be abstract number 908 from Japan Industry Technology Institute. Dr. Nagai will present.
Good afternoon, Mr. Chairman. I'm Tomo Nagai. Please use my video, please.
Infang?
Use my video, please.
Can you?
Good afternoon, ladies and gentlemen. I'm Tomo Nakai. Today's my talk is titled as Functional Property of Adjacent Narrow Thin-film Strips with Inclined Uniaxial Magnetic Anisotropy. This is the outline of my presentation and about my institute. Okay, this sheet shows a concept of functionality of my presentation. A system that consists of dipole moments has a certain effect of mutual interaction inside the material. It affects the material property such as the deformation strength, a propagation of vibration caused by the interaction of each moment. If the moment is able to be erased by an artificial procedure, the property of the material is drastically changed and a new functionality will be provided to the material system. We have already established the transition phenomenon of moment using a magnetic microelement. A magnetic element is well known for it has a magnetic dipole, and the dipole is able to switch the direction by controlling the external magnetic field. The element we propose here have a moment of magnetic dipole, and it is also possible to erase it by making a magnetic inner structure in it by applying an artificial stimulation. The point of this transition phenomenon is that it would not appear until the artificial stimulation would apply to the element. Let me explain the physical details of this transition phenomenon. The upper left schematic shows the state diagram of this phenomenon. It is a magnetization diagram in which the horizontal axis represents the applied external field and the vertical axis represents the magnetization of the element. The applied field is a magnetic field which is along the length direction of the element. It's well known that a soft magnetic strip element having a needle-like shape is dominantly affected by the field along the length direction due to the demagnetizing force. The element that has a variation of state, as shown in this diagram, apparently switches between two states. There are the magnetic dipoles with opposite directions plus and minus. This transition phenomenon is well known as a magnetic switching. The difference between the ordinary magnetic switching and our proposed phenomenon is the existence of much domain state, and which is not ordinarily appeared. We call this state as a hidden stable state. The stable means that this state has a lower energy compared with dipole state. This hidden stable state exists in the condition when the magnetic z-axis lies in the direction almost in the 70 degrees against the width direction of the element. These figures are experimentally obtained results. The 60 degrees z-axis makes the three states existing around the zero external field as shown in the left figure. The domain transition that changes to multi domain originated from the single domain appears as the position of red arrow. When the angle of z-axis increases, the transition point of the domain state moves as shown in the right figure. Eventually, the multi-domain state would become a hidden state. It's around 70 degrees of z-axis. When we reach to this point, questions would be noticed, such as, does a hidden state actually exist? And how to make transition to the hidden state? The questions would be solved by applying the distributed normal field. The lower right schematic indicates it. The hidden state is able to appear in the case when a distributed normal field is applied. The inset of this schematic explains the distributed normal field, which is the surface normal field of the element substrate having a partial vector of in-plane field proportionally changing as a function of the longitudinal displacement. This magnetic state transition was also simulated by a domain structure analysis. The assembled domain structure model, ADSM, was applied to this element, and we obtained the same results as shown previously. It was collaborated with Professor Matsuo, Kyoto University. We have carried out many experiments as follows. As a result, we can say that the artificial transition to the hidden multi-domain state was confirmed and established for this element. An application of this phenomenon was proposed. A magnetic sensor with memory function is it, and this sheet shows the operating principle diagram of the sensor. The initial state is a multi-domain hidden state, which is an energetically stable state. When an external field that is larger than the threshold field of domain transition is applied, the state changes to single-domain dipole state. This state would be kept even after the applied field was erased. Therefore, this sensor memorizes the event of magnetic field application. When a distributed field would be applied, the memorized state can be reset to the initial state. Now let me introduce the case of multiple elements. This sheet shows an experimental result for adjacent elements having the hidden state. The 20 micrometers width and 3000 micrometer length elements were adjacently aligned with the line space as 20 micrometers and 20 micrometers. The result shows that the elements in the adjacent layout still have the same property as a single element having the hidden state. The element switched the direction of dipole as changing the external field. The magnetic mutual interaction between elements makes the direction transition gradually as if they were affected by the demagnetizing force. When the distributed normal field was applied, the transition towards the multi-domain state was observed as shown in the right figure. This is the last data of my presentation. A high-frequency permeability of the adjacent nanostrips is shown. The data of theta equal 71 degrees, which are surrounded by red line, is the issue. The dipole state has a slight permeability, whereas the multi-domain state has a relatively large permeability in the frequency range from 10 to some hundreds of megahertz. It also switches both the real and the imaginary permeability. Then this result shows that the switched domain of the element is a candidate of a switched inductor or a switched electromagnetic metamaterial for high frequency application. This is a summary of my presentation. Thank you for your kind attention.
Thank you, Dr. Takai.
Thank you.
Next paper will be abstract number 330 from France, University of Paris and the Sorbonne University, and also Institute of Nanoscience in France. Presenter will be Dr. Kazayos. Please present.
I think the presenter is not here.
Okay.
Yeah, we have the videos.
Do you have a record? Okay, thank you.
Hello, I'm Maximilian Kazayos from University of Paris, and I present you our work on elastic properties in the multi-probe bismuth-fluoride biprobe method. We work in collaboration with Laurent Belliard from Sorbonne University, Philippe Gemia for the simulation from University Paris Nord, and Dorothée Colson from Saclay for the samples. This work has been published this year in Applied Physics Letters. As you know, multifluoric materials have several spheric order, which in many cases interact. There are many studies on magnetoelectric effect, but few works on magnetostriation. However, one knows the important effect of stresses on magnetic and ferroelectric processes in synthesis, for example. In order to control the effect of stresses in multifluoric materials, it's necessary to know its elastic properties through the elastic constant. We realized that apart from a few numerical words, the experimental words were counted on the finger of one hand. So in this study, we have worked on single crystal of one of the most known multifluoric bismuth fluoride. The single crystals are synthesized by a fixed method at Saclay by Dorothée Colson. Bismuth fluoride is ferroelectric below 1100 K with a huge polarization of 100 micron coulomb per centimeter square along the 111 direction of the pseudo-cubic structure. It presents also a high resistivity. BF4 is also antiferromagnetic below 640 K, and due to the Jalovsky-Moria interaction, the spin form a cycloid in the -1 to -1 plane. To determine the elastic constant of BF4, we have used a time-resolved acoustic technique, which has been developed in the 80s. This technique has really taken off with the development of high-performance pulse laser sources. And the acoustical pump and probe technique is an optical method that generates short acoustic pulses, which can be detected by time delay probing. And due to the large frequency bandwidth of the acoustic pulse, it is thus possible to study materials at a sub-micrometer scale. This time resolved measurements allow to measure sound velocity with an accuracy typically better than 5%, and thus to determine the related elastic properties. So acoustic measurements were performed using a standard stabilized Michelson interferometer sensitive to the perpendicular surface displacement. A 12 nanosecond maximum pump and probe time delay is achieved using a mobile reflector mounted on a translation stage. Both the pump and probe beams are focused with a microscope objective with an mirror aperture of 0.9 fixed on a piezoelectric stage. So this figure shows the propagation of the acoustic wave on the bismuth ferrite surface. The signal is recorded by scanning the surface of the sample at fixed Pumper probe delay. It corresponds to a snapshot taken at 3.6 nanoseconds from the coincidence. The white area in the center of the image is a used stationary photothermal component, and the contrast in intensity correspond to maxima and minima in the amplitude of the waveform. So we have performed scanline along three independent directions to obtain the profile of the acoustic wave at different time of probe arrival after the coincidence. So the next figure presents the relative phase change of the electromagnetic field of the probe along the scan direction 1 as a function of the probe position for several probe time delay. One can observe in this figure three peaks whose positions evolve as a function of the probe delay. These peaks correspond to wave amplitude maxima and three distinct propagation speeds. Thanks to BF4 symmetry, only 7 independent elastic constants have to be determined. And to do that, we are calculating the first set of elastic constants using DFT calculation. This step of constant is then used in an article equation of acoustic modes. We can thus determine with the Christoffel equations 4 theoretical velocities: the longitudinal mode, the fastest transverse mode, the slowest transverse mode, and the Rayleigh surface mode. The values of the elastic constant are optimized by minimizing the difference between the experimental and theoretical velocities. Finally, we have determined all the constants of BF4. So here you can see the final set of the obtained value. So now I present the calculate an experimental velocity associated with the three bulk waves and the surface wave as a function of the phi angle. This black line corresponds to the calculate longitudinal velocity, and the square represents the experimental point. The vertical lines are associated to the three directions of measurements. So here, the comparison for the fastest transverse mode. Now the experimental and calculated velocity for the slowest transverse mode. One velocity along direction 2 is below from the calculated bulk shear velocities. And to find an explanation for this apparent discrepancy, we have calculated with a homemade program the generalized Rayleigh surface wave for semi-infinite anisotropic elastic medium. And one can see the good agreement between the experimental velocity and the calculated surface acoustic mode, even if this comparison is only based on this unique analyzed experimental. And finally, we have front curves within the surface gauge in the plane that can be compared to the time resolved images. Here's the longitudinal acoustic phonon in black is too fast and is no longer present in the image, while the other slower waves are recorded. In the polar representation, we can clearly see a flower shape reproducing the experimental pattern with 4 petals in the vicinity of the same direction. So there is a nice agreement between the experimental results and our calculation. To conclude, we have implemented acoustic pump and probe experiment at the nanosecond time scale on bismuth ferrite.
Good afternoon, ladies and
Oh,
gentlemen.
sorry,
I'm Tomo
make
Nakai.
a mistake.
Today's my talk is titled as Functional Property of.
Thank you. Next
Sorry.
paper. Hello? Inform.
Yeah, we can
You want to say
hear you.
something?
Oh, no, because the time
Okay.
is up.
We will move forward, right?
Yeah.
Okay. Next paper, abstract number 524. That is my paper. Let me share my PowerPoint slide. Everybody can see it? Yes? Infang, can you see my paper?
No.
Okay.
No, sir. No.
Just a minute. Screen share. And then go back. How about now?
Yeah, we can
Yes.
see it.
Yes.
Yes? Okay, thank you. All right, title of my paper is Revisiting Most of Our Spectroscopy Characterization of Magnetic Materials from University of Alabama, Wonkwang University, Seoul, South Korea, and University of Pittsburgh, USA, and also Material Science and Engineering Department, Tokyo Institute of Technology, Japan. This is the, you're looking at the most power system here. So this is the most power system consists of gamma radiation source here and the sample here and proportional counter. That means the analytical tools for observe the gamma ray by for example, the barium ferrite right here. And then pulse detect source. Once we have isotope cobalt decayed to ground state, you will expect a 4.4 kiloelectron volt gamma ray. This gamma ray hit this sample right here in the blue color here. And then this gamma ray observed some energy, some other energy transmitted. The transmitted energy will be proportionally detected with the pulse detector. And what kind of a spectrum we are expecting from this gamma ray radiation on magnetic materials? We have three different spectrum. One is isomer shift, a single spectrum, and a double spectrum is 6 spectrum. Normally, single spectrum called isomer shift. And couple of spectrum is called quadruple splitting. And the last, the high profile field means the 6 spectrum. That's observing sample will have combined single, double, 6 high profile field spectrum. And then we have to analyze individually. Therefore, we can have a magnetic property out of this sample here. So next one. Right here, more details. This is the magnetic history. This sort of normally we measure by sample by magnetic sample by barometer here. And we are interested in the saturation magnetization and coercivity. That saturation magnetization and coercivity can be predicted by this most power spectra. Most power spectra, as I said, consists of 3 different spectrum here: single, double, 6. Why 6 spectrum we observe? Because the transition from excited state to the ground state, we have 1, 2, 3, 4, 5, 6 spectrum here. That's why we are observing this. When we analyze this and that, we can predict some magnetic property of your observer. Let's go back to what's the isomer shift, otherwise named chemical shift delta. That is the S electron density between the source means the gamma ray right here, and the observer. In this case, we use the barium ferrite sample here. Once you measure isomer shift, you can have an ion charge balance, +2, +3, whatever. And then if you analyze 2 spectrum right here, that is the QS means quadruple splitting. Quadruple splitting means the delta. a shift in nuclear energy level that is induced by an electric field gradient caused by nearby electrons. That means we can have information on degree of crystal distortion. Crystal distortion means the magnetic anisotropy energy. Once you see the magnetic anisotropy energy information, then you can predict the coercivity as measured by magnetic magnetometer. And the next one, this is 6 spectrum means a hyperfine field. Hyperfine field means actually magnetic materials sectors and magnetization. Identification of a substitute site, sublattice, we can do that. And also we can measure Curie temperature or nil temperature, like what we have done with the Brownian function to calculate the temperature dependence of magnetization and the temperature dependence of magnet flux. Next, how do we understanding this, the most of our spectroscopy? What kind of a parameter we will expect and how? How do we calculate isomer shift, quadruple splitting, hyperfine magnetic field from this spectrum? We have a six peak, and the different peak has the different velocity here. Why we say velocity? Because this gamma ray source will be moving forward and backward in between the minus v velocity, positive v velocity. In this case, we control this velocity of this isotope, cobalt isotope carrying car between minus 11 millimeter per second and plus 11 millimeter second. Why we are talking about millimeter second? In most of our spectral society, we used this millimeter per second as a velocity as the conventional energy. So we can think about the V means the velocity of this isotope carrying car means the energy. Therefore, we can calculate the isomer shift as follow this one: B1, B2, B3, B6. You can identify the B1, B1, B2, B3, B4, B5, P6. And then once you detect that number divided by 2, that gives us the isomer shift. And once the isomer shift number obtained, we can understanding what the balance of state of ion in your compound. Quadruple splitting case that we can calculate from major most of our spectroscopy. B1 minus B2 and minus B5 and B6 divided by 2. That gives us the quadruple splitting. Quadruple splitting number is getting higher. That means that your magnetic anisotropy constant is getting higher. That means the coercivity is getting higher. Finally, a hyperfine field, we can calculate the 3.1047 times the B1 and B6. Then you can, if you have a big number for hyperfine magnetic field, that means the magnetization of your sample is much bigger than a smaller number for hyperfine magnetic field. This is the more details here. So we have A1, A2, A3, A4, A5, A6. This is the area 1 of first peak, area 2, second peak, so on and so forth. And then this area range normally can be calculated by that formula right here. And 1 and 6 is identical area. 2 and 5 areas remain the same. 3, 4 remain the same. Depends on the angle right here. Gamma ray direction make an angle against the c-axis of this hexagonal structure right here. So once you change this gamma ray direction toward your sample, you can control A1, A2, A3, A5 of that area density. And then you can predict predict the angle between this c-axis and the gamma ray directions here. And likewise, you can apply this gamma ray in parallel with this applied field here, and then apply the field. In this case, you can have a different A1 through A6 ratio is different. Next one, let us take, for example, M-type hexaferrite. M-type hexaferrite, 5 different magnetic sites. Individual site induced 6 spectrum, 6 peak, and the 6 peak times the 5, then means the 5 times 6 means the 30 peaks will appear from hexagonal barium ferrite, such formula like this here. So we will analyze the 30 peaks out of the MOSFET spectrum to understand isomer shift, hyperfine field, and quadruple splitting. Finally, we will predict the magnetic crystalline anisotropy constant and the saturation magnetic moment. This is the practically experimentally observed spectrum right here. This looks like a very few number of peaks, but that spectrum include 30 because this is the barium ferrite powder here. So we analyze this, and then we can have isomer shift and the saturation magnetic hyperfine field, quadruple splitting, and turn those parameters into the magnetic properties. Once you have very complicated this system, and then we can apply the magnetic field with the direction of a gamma ray or a perpendicular to this, and the sum of this peak will be disappear. Because of this, we can understanding magnetic property changes and the magnetic hyperfine field changes with some substitution site or interstitial site in the case of hexaferrite. This one is also from barium ferrite. Once we apply the different angle, this gamma ray against the C-axis of hexaferrite, you will see the different hyperfine field here. Look at here, this hyperfine field from here, the V1 and V6, much larger than that. That means the magnetization is much larger than that. Depends on the applied magnetic field against this C-axis of hexaferrite. Next one is the you can apply the most power spectroscopic characterization to nanocrystalline soft magnetic materials. This is a nanocrystalline soft magnetic materials. You can characterize this to a core and interfacial site and amorphous metric site. Once you analyze the most power spectra, you can identify amorphous metrics right here, and this spectrum from interface between amorphous matrix and crystallite, in this case, iron silicon, and then this is the overall total spectrum here. So what most of our characterization tool is fantastic to understand the nanocrystalline structured soft magnetic materials as well. Another one is the most of our characterization is monoclinic ferromagnetic iron selenide. Iron selenide crystal structure looks like that. Even most of our spectrum can give us the information, the angle between this one and that, or this one and that. We can predict the angles right here from analysis of this most of our spectrum. This is the most of our spectrum for iron selenide. This is the 70 nickel nitrogen temperature here. And once increase the sample temperature from 78 to 320 K, and then this multi peak becoming very few peak. And it looks like a single peak. That 320 K is called the nil temperature. Otherwise, the Curie temperature right here. This is the room temperature. They have magnetic hyperfine field between this V1 and V6 is much larger than that. And then you can estimate which spectrum coming from which magnetic site, because the iron selenide has 2 different site, magnetic site. A is 2A site, B substrate coming from a 4A site. And then this is the 2A side magnet high-power field like that, and the B side magnet high-power field like that. And also we can analyze this spectrum and that spectra to identify the quadruple splitting. As you see here, B side is a quadruple splitting fairly higher than that. That means the B side ion has been more distorted than the ion situating at the A sublattice right here. That's what we can understand that. Next one is the powerful tool of this most of our spectrum can identify the modern temperature transition temperature. Modern transition temperature means a flip-flop temperature. How can we measure this? This is the quadruple splitting in terms of temperature. And this 0 point below is negative, above is a positive quadruple splitting. At 220 Kelvin, that quadruple splitting change its sign from positive to negative. That is called modern transition temperature. Once we see the modern temperature of 40 nanometer hematite nanoparticles, and then we identify the modern temperature, originally magnet field right there, and the modern transition temperature nearby. This is the magnetization going that direction. And we identified that angle between this z-axis and that shift magnetization direction as the 28 degree. So most of our spectrum can tell us the flip-flop angle as well. In the summary, most of our spectroscopy can tell us the ion shift to chemical and quadruple splitting, magnet high-power field, modern transition temperature. Therefore, there's the most of our spectroscopy is a very powerful tool to characterize magnetic field. Thank you. Next paper will be abstract number 206 from Zaman University College from Saudi Arabia. And Dr. Fahmy. Dr. Fahmy here?
We have a video here.
Okay, can you turn on? Thank you.
Welcome everybody. Our paper title, A New Boundary Element Formulation and Analysis of Fractional Order 3 Temperature Nonlinear Generalized Thermoelastic Problems of Functionally Graded Magnetic Thermoelectric Materials. The main aim of this article is to introduce a new fractional order theory to contribute for increasing development of technological and industrial applications of functionally graded magnetic thermoelectric materials. This theory, called 3 temperature nonlinear generalized thermoelasticity of functionally graded magnetic thermoelectric materials. In order to guide the current research field to the development of new functionally graded materials, we should successfully implement the computerized numerical method that will be solved to and simulate difficult nonlinear functionally graded material problems. The governing equations of the proposed theory are very complex to solve experimentally or analytically because of very strong nonlinearity. To overcome this, we need to develop new numerical technique for solving such equations. Therefore, we propose a new boundary element method formulation for solving the theory's governing equations. Due to the advantage of the boundary element method solution, such as treating problems with complex shapes that are difficult to treat with traditional methods and doesn't require the discretization of the interior domain. Also, it requires low CPU and low memory storage. Therefore, the boundary element method is suitable for treating a wide range of advanced functionally graded magnetic thermoelectric materials applications. The numerical results are presented highlighting the effects of magnetic field and graded parameter on the thermal stress. The numerical results also confirm the validity and accuracy of the proposed technique. Formulation of the problem. The governing equations for fractional order nonlinear generalized thermoelastic problems of functionally graded magnetic thermoelectric materials can be written as equation 1, equation 2, 3, and 4. The fractional 3 temperature radiative heat conduction equations can be expressed as equation 5 with equation 6 and 7. The total energy of the unit mass can be described as in equation 8. Boundary element method simulation for temperature. Equation 13, which can be written in the absence of internal heat source as equation 14. To transform the domain integral in 14 to boundary, we assume that the time derivative of temperature can be approximated with a series of known function and unknown coefficients. Equation 15 and 16. Thus, equation 14 results in the following boundary integral equation 17. Where equation 18 and 19, in which the answers are coefficients of, as in reference 34, using the standard boundary element discretization scheme for equation 17 and using equation 19, we obtain the following set of ordinary differential equation 21. 21 is a system of ordinary differential equation. The diffusion matrix can be defined as in equation 22 with equations 23 and 24. In order to solve equation 21, numerically the function t, alpha, and q are interpolated as equation 25 and 26, where the parameter theta determines the practical time in the present time step. By differentiation equation 25 with respect to time, we get equation 27. By substituting from equations 25, 26, and 27 into equation 21, we obtain 28. Making use of initial conditions and boundary conditions at delta t and considering the previous time step solution as initial values for next step, we obtain the following system of linear algebraic equations 29. BM simulation for displacement field. The governing equations 1 and 2 using the weighted residual method can be transformed equivalently into the following integral equations 30, in which 31 the boundary conditions are 32, 33. The integration of the first term of equations 33 and 34 leads to, according to Huang and Liang 41 reference, we can write the boundary integral equations 35. The integration of the left hand side of 35 by parts leads to equation 36. According to Ehringen, the elastic stress can be written as equation 37. Hence, equation 36 may be expressed as equation 38 by applying the integration by parts. Again, to the left hand side of 38, we obtain equation 39. The weighting functions for U equal delta n and Vi equal 0 may be written as follows. Equation 40. According to Dragos, the fundamental solution may be expressed as in equation 41. The weighting function for Ui and the Vi delta may be expressed as follows. Equation 42. On the basis of Dragos, the fundamental solution may be expressed as in equation 43. Using the above two sets of weighting functions into 39, we have equations 44 and 45. Equation 46, where now we introduce the following relations. 47, By discretizing the boundary, we can write 46 in the following as in equation 48. By employing the following formula, equation 50, we can write equation 49 as in equation 51. The global matrix system equation for all I nodes can be written as equation 52, where Q denotes displacement and B denotes attractions. Now we can write 52 into the following form: 53. Geometry of the current problem. Boundary element model of the current problem. Xrd shows variation of the thermal stress sigma 11 along the x-axis for different values of fractional order parameter. It's for fractional order parameters: 0.3, 0.6, 0.9. Variation of thermal stress with fractional order parameter. This thermal stress sigma 12 for different values of fractional order parameter: 0.3, 0.6, and 0.9. A 0.3, 0.6, 0.9. Variation of the thermal stress sigma 22 along the x-axis for different values of fractional order parameter. Variation of the thermal stress sigma 11 for different values of functionally graded parameter M 0.3, 0.6, 0.9. Also, variation of the thermal stress sigma 12 along the x-axis for different values of functionally graded parameter. And variation of the thermal stress sigma 22 along the x-axis for different values of functionally graded parameter, as in Fig 8. In order to validate or verify our results with the suggested method, we compare our results for a special case with finite element results and normal mode method. We get good agreement with other results for boundary element method. Also sigma 11 for different method, BEM, FEM, MMM, where fractional order equals 0 and functionally graded 0.6. The primary goal of this paper is to present a novel fractional order theory that will aid in thermoelectric materials is the same given to this theory. We must successfully adopt computerized numerical methods for solving and simulating complex nonlinear functionally graded material problems in order to guide the current research field toward the development of new functionally graded materials. Because of its severe nonlinearity, the suggested theories governing equations are extremely difficult to solve experimentally or analytically. To solve this, new numerical approaches for solving such equations must be developed. As a result, we suggest a new formulation of the boundary element method for solving theories governing equation. Because of these benefits of boundary element method approach, such as ability to solve complicated shapes problems that are difficult to deal using standard methods, and the lack of the need for discretization of the internal domain. It also necessitates stacks of at low CPU utilization and memory storage. As a result, the boundary element is appropriate for addressing a wide range of sophisticated applications. The numerical results are presented emphasizing the impact of magnetic field and graded parameter on thermal stress and functionally graded. The numerical findings also validate the proposed formulation and solution techniques and validity and accuracy. Many thanks. Many thanks.
Thank you, Polly. Next, the paper will be abstract number 545 from IIT Madras, Chennai, Dr. Rao. One thing I want to mention, we skipped the abstract number 164 because my printed program schedule doesn't include that. I missed that. I apologize that. And we will print that 164 at the end of this session. Will it be okay, Jing Fan?
Hi, Professor. We don't have the video of that speaker. So if the professor is not in this room.
Okay, Dr. Lau here for 545. Paper number 545 from IIT Madras, Chennai, Dr. Rao. Are you here? So, Jin Fan, do you have recorded a presentation for paper number 545 and 164? Do you have those?
Sorry, can you say the professor name or the title of
paper number 164 and 545?
Sorry, we don't have their video. We don't have the video.
Oh, for both. So Dr. Rao didn't attend this meeting yet?
Yeah, we don't have Dr. Rao's video.
Oh, I cannot see his name on screen. So that means we have to.
Dr. Shi?
I'm sorry, in front.
We have the video of Dr. Shin. The next.
Oh, next paper.
Yes, the progress in developing macro multilayer. This.
No, it is time for us to present paper number 163 from IIT Madras, Chennai, India. 163. You don't have any recorded presentation.
Yes, we don't have the we don't have the video.
Oh, so he's not attending this session yet. So that means we have to wait until 5 o'clock to start paper number 545. So we have to wait 4 minutes before starting again, abstract number 545 from Demlet University, Egypt, and Ain Shama University, Egypt. So we have to wait this paper until 5 o'clock. Will be okay, Jing Fang?
Sorry, Professor, we have the video for 4:50 to 5 o'clock. We have this video.
So we don't have any 545, 163 paper yet. Though recorded presentation also, he doesn't attend this meeting either, right? So our next paper will be for 545. We'll begin at 5 o'clock. So we have to wait 3 minutes. Right?
Okay.
Good.
Okay.
Good day. This is Professor Volker speaking.
Professor Rao here? Oh, good. He's here?
So the paper called Strain Optronics on 2D materials with a twist at 5 p.m. will be given by myself. I'm Professor Zorger, and I'm looking forward to that.
Oh, you are the let me see. You are the Dr. Abu Alamat?
No, I am Dr. Abul Magd. I think Dr. Volker is just before me.
Well,
he's first, and I'm
okay. 5 o'clock.
We still have to hear Mr. Shin. We still have to hear Mr. Shin.
Well, now it's the 4:58. So we will start to abstract number 545 at the 5 from Egypt.
No, according to the
Dr.
program.
Shin is here.
Go ahead, Jing Sui.
Dr. Shin, I think Dr. Shin is in this Zoom, but I messaged him. He didn't reply. Oh yeah, he's here.
I'm not understand the.
Hello.
Oh yeah, Dr.
Oh,
Shin.
Dr. Shin.
Yeah.
Yes.
Yeah, this is Shin.
Yes. What's your abstract number?
I don't remember this. I think it's a 544.
5:44. Yes, we'll begin at the 5 o'clock.
Okay. But I'm joining with my cell phone now, and I submitted the recorded video. So would you please run the video?
Okay.
Okay.
I have a question. At 5 p.m., the online program says it is my talk. I'm Professor Zorger. It says 5 p.m. to 5:15. Strain Optronics. Did somehow the calendar shift? I have the website open right now. I'm just curious.
Oh, okay.
Yes.
What's the abstract number?
We have to. Here,
I'm
Professor
not
Pignoli,
sure.
we are 10 minutes late.
Dr. Shin, your abstract number. What's your abstract number?
I think it's a 544, and my talk is 750, right?
544.
That's right.
What's that 544? I don't have any printed paper here.
Huh. According to the schedule, my talk is supposed to be on 750.
750?
Right. Well, 450 Pacific time.
I mean, I'm talking about the Eastern time. Yeah, 450.
Oh, we are talking about California time. 5 o'clock in California time.
Right.
5:45 paper will be presented from Egypt.
No.
Jingfa, can you correct me if I'm wrong?
No, you don't have the right program.
I think Dr. Shin's present will be 4:50 to 5 o'clock, and we have his video already.
Yeah,
and
right now it should be 5:45.
Yes, and shall we just give we just quickly go over Dr. Shin's PowerPoint, and then we can move to
لسه يا دكتور لسه.
Let me see. I'm looking at the printed
schedule.
Program here, schedule. Yes, I'm look at my own printed schedule.
No, well, that's not the right one.
Okay, sorry. So that now
we are
it's
here now,
5 o'clock.
and Dr. Volker is here.
Maybe shall we from just start from Dr. Walker, and maybe next time if the presenter is not here, we can play Dr. Shin's video at that time. Is that okay?
Why is that different from my printed schedule here?
Oh yeah, we can follow your schedule. Shall we just begin from Dr. Walker's talk on 5 o'clock.
So
and,
can we talk
the
about
following,
the abstract number rather than names? Abstract number. What abstract number for Dr. Shin? He said.
You can see his report is from 4:50 to 5 o'clock. It just passed. Shall we? But we have his video. Shall we just keep the video? And if later if the speaker, some other speaker is not here, we can use the time to play Dr. Shin's video instead.
So we will skip 163 abstract, right? Is that correct? Dr. Rao from IIT Madrid.
No.
Yeah, he said no. What's the correct then?
Yeah, you can see. Hello, Professor. You can see from your screen. Our schedule is all the same. Because now it's 5 o'clock p.m. Shall we start from the screen optronic
strand tonic 2D material?
Yeah. Shall we start from this talk, and later we can play we can play last video if we have extra time.
Okay, which paper should be presented this time, Jinfa?
Dr. Walker is ready, I think.
Okay, Dr. Walker,
yes,
you go ahead. All right.
All right.
Good. All right, thank you.
Excellent.
My apology.
No worries. Let me turn it on. And well, it's a great pleasure to present our work here for this conference. Good day, good morning, good evening, everybody around the world. My name is Volker Sorger, and I'm a professor at George Washington University. I'm also the founder of the deep tech startup Optelligence. Today, I will talk about strain optronics. And strain optronics is a new way for 2D materials with a twist to engineer devices and have interesting effects. Strain essentially arises from taking a material or a rod and extending it by a certain amount. Let's call this, for instance, from L to with an extended distance delta. The strain thereby induced is simply the ratio of delta over L based on a force here we call P. And the stimulus naturally leads to a response. So the stress leads to a strain, meaning the force is proportional to a certain strain. The proportionality constant between this we call Young's module. That's basically what we show here. Amount of stress versus strain for various materials, we find these very soft materials, and then we find very strong materials. For instance, steel is one of the strongest materials out there. Turns out two-dimensional materials are even stronger, which suggests they could be very well used for straining. The force, meaning the stress, versus the displacement, the strain, in this Young's module essentially is linear, but only up to a certain point, at which the material starts to yield or break and start to fracture at a point eventually. 2D materials are very exciting for this perspective because we can actually strain the material very dramatically, up to 1 terapascal. So that is even higher than for steel, which means we can strain them to about a few percent of the material. Now, straining conceptually in optoelectronic devices is not new. We have been doing this for several years. This is the Intel's Pentium 4 processor, 20 years old already. And what they did is, for instance, here at this point, they basically strained the material so the light hole moved above the heavy hole such that we can have a very high mobility or higher mobility, because of course we all know this mobility is inverse proportional to the effective mass. And this is addressing in silicon, for example, the low carrier mobility in for p-dope material and for n-dope. What about 2D materials? Well, there are multiple ways we can strain them. For instance, we can add in strippers topology, we can add some sort of X structures, and we overlay this with 2D material. We can use indentation, we can bend the structure, sort of using PDMS, and then we can basically flex it and bend it. Now, why should we consider 2D materials for optoelectronic devices, meaning electro-optic modulators, photodetectors, maybe lasers? Well, it turns out that if you do an analysis for optoelectronic devices, something we did a couple of years ago, and you ask fundamentally, does the performance of a device improve? For instance, in a modulator, you want to have a lower energy per bit, and the energy per bit improves with something known as Purcell factor. The Purcell factor is nothing else but the volume, the Q factor of this underlying system divided by the mode volume. This V is the mode volume, which suggests if you have a very small material or small optical mode, you can basically have a very efficient device. Similar for the gain bandwidth product of a detector can be also improved with Purcell factor. So 2D materials are now very, very synergistic for these sort of nanoscale modes. This is a cross-section here of a plasmonic hybrid mode, for example. They have interesting new physics. They are electro-optic tunable. They're composition controllable. They are patternable with orthography, and they do not require any lattice matching on a substrate. So unlike 3.5, you can really basically put them on any substrate. It's a bit of a challenge to transfer them without cross-contamination. That's something we recently solved. So typical systems basically using a flat structure when you transfer them, let's say on a photonic chip, for example. So yes, you get this particular flake here on this ring resonator, but you also get a lot of like other parts that you don't like. Now, what we can do here is we can use this microstamper approach on the right here, and we can very synergistic, but very uniquely only transfer one material without cross-contamination. So here is a little video that basically shows this. So zooming down now to the chip. So here's a chip, and you see here the photonic waveguide, and you see your pre-etched or pre-prepared contact. Right on this location where the transfer to the material. We zoom up now to the PDMS on which the 3 materials are placed, and we want to transfer only this green flake and not all the other ones. So what we do, we take a microstamper, we align this microstamper with this 2D material and with the underlying contact structure, let's say of a waveguide. We press it down, we release it, and we can basically transfer this. And what I'm really excited about to share here is that this time we see here 30 seconds, 40 seconds. This is actually live. So graduate student is actually turning the knobs and filming at the same time. Now, let's talk about some now with this technology and this train idea about some devices, in particular photodetectors. So this was a paper we published last year, where basically we take a light signal, we couple this to a photonic ring, and notice here now it's wrapped around this bended to the material. This introduces strain, and now you see here we have these blue and yellow carriers, meaning we can separate the charges, electrons from holes, and we can have basically photocurrent collecting the charges from here and from here. Notice here in the back, we have another 2D material on top of a waveguide here, but it's flat, it's not strained, and therefore here we actually, once we send light through, we do not obtain any any light absorption, so it's quote unquote dark. This is basically shown here in more detail. So here's this wrapped around structure. It's MOT2. Overlap factor is about a few percent. Here's some images. If we do an IV curve, if we do not shine light at the structure, we have a pretty low dark current. It is about 1 to 2 orders of magnitude lower for graphene, actually even up to 3 orders of magnitude lower than for graphene, because graphene obviously has no band gap. So you always have like basic carriers moving across. So this is a very nice low dark current, which is very nice. And then you see the on-off ratio is about like 10 to the 2, 10 to the 3. We were curious why this device actually works, because the light we send in this waveguide here is 1550 nanometer. This is basically 0.8 EV. But the band gap of this MOT2 material here essentially is 1 EV. So we were in the band gap. So why did we see absorption? Now we performed a control experiment. Basically, we have a 2D material here, the same 2D material, that is flat. For this case, we do not observe any photocurrent as a function of voltage and optical power. Notice it's all blue. There's basically no photocurrent down here. Once we strain it, so we wrap it around, we strain it, we have a pretty high photocurrent now. Notice this data appears experimental data, simply binned, as opposed to this is not simulated data. Then we verified this strain effect by performing Kelvin probe force microscopy. This allows us to basically map out the work function as a function of strain. And then we can use density function theory to use the amount of strain, notice a few percent, that's very high, and basically performed band gap simulations. And we found indeed, when it's not strained, it is 1 EV, meaning it's transparent for our 0.8 EV telecom wavelength. Once we strain it, we lower the band gap dramatically to 0.8 eV. We measure the speed of this device. It's about tens of megahertz. It matches what you expect, basically given by the carrier transit time, fundamentally. The noise equivalent power, NEP, it's the power to get a signal to noise ratio of 1 at 1 hertz. So lower is better, obviously less power to get to an SNR of 1 is good. And we notice here we just need 90 picowatt per square hertz. And this is about a factor an order of magnitude lower than for graphene, simply again because the NEP is proportional to the dark current. So lower dark current is basically great. Now then we went on and we performed an experiment with where we strained this material even further and did basically IV tests. So here we checked, we put an AFM chip and we mapped this IV curves locally. We did a local mapping now. And we find indeed, if you look here, the conductivity as a function of location really dramatically shifts. So you notice here at the edge of this waveguide, the waveguide is roughly about here. This is the structure of this waveguide. At the edges, the strain is higher and is lower on the on the sides. And then when we basically perform some modeling of these functions, this current now, we can extract this phi. This is basically the actual work function. So we can plot the work function as a function of spatial location. And notice now, essentially, this allows now to tune the Schottky barrier height. So now Straintronics essentially not only allows to tune the mobility and the band gap, but also the Schottky barrier height. So it's a very powerful tool. And this work has just been accepted actually this week at this paper here. And then lastly, talking about scaling length theory. So we're borrowing the idea from field effect transistors to build very efficient opto-electronic devices, in particular detectors. The gain band of the product is given by the gain. This is the carrier lifetime over the transit time divided by the carrier lifetime. You notice carrier lifetime cancels, so you're left with the transit time. Transit time is the time an electron takes to be collected here by your source and drain contacts. If you make your length, this L, very, very short, and you order of like tens of nanometer, like a plasmonic slot, now your transit time can be in a picosecond, which would be like basically approaching like a terahertz. We can map this out in detail now. This is basically here showing the transit time limited and RC limited photocarrier speed as a function of channel length, meaning source drain distance. And notice in each time you're limited either RC or transit, and for various mobilities and for various resistances. And here's a very interesting regime. If you look at this one, we can basically, with a very modest, in fact, I put it on the right here explicitly, with a very modest resistance and mobility, you can actually get up to 100 gigahertz fast devices if you make it like the channel length very narrow in the order of tens of nanometers. And on the right here, we're showing the gain or the responsivity, which is the bandwidth for all devices that either are slow and sensitive or fast but not sensitive. And with this now, we are actually pushing into this sensitive and fast regime. And here's an initial work on this direction using graphene, where we basically show the responsivity versus compactness in these plasmonic slot structures shown on the right. This is actually, these work from this. And then some very nice work that is still unpublished is where we put now a like in TMD material into this slots. So basically we make these very, very narrow slots to utilize this high gamma product. Here's the IV curve. We see we get a nice photo response. And indeed, if we reduce the slot distance, we basically are able to get a very high overlap factor and a very good mobility, a very good like responsivity. We experimentally showed we can get to up to 10 gigahertz fast devices like this, and they're significantly faster than for a long channel device. So again, this is the data point from this. This is again still unpublished. I'm happy to share this with you today here. And there is room for improvement. If we can improve the mobility a little bit more, we basically can get up to 100 gigahertz fast devices. And then very finally, this is the last work. We also perform PN junction devices now, introducing a built-in potential, which means we can drive these devices without voltage. And this allows us to get an extremely low dark current of 0.1 picoamps. This is obviously very great for lots of coming work. With this, happy to summarize, I introduced why 2D materials are important. I introduced a two-dimensional printer for nice and clean transfers. I introduced Train Optronics to engineer mobility, bandgap, and the Schottky barrier height. And I showed the slot scaling approach for these very high gain band product detectors. Happy to take any questions, and you can email me here to the conference, and thank you very much.
Thank you, Dr. Sorber. Next paper will be presented by Dr. Rao from IIT Madras, Chennai. Dr. Rao is there. Jinfang, you said before we don't have any recorded presentation, right?
Yeah, I think Dr. Rao is
yes,
not here.
You said yes.
Dr. Rao isn't here and he didn't provide the video.
Okay, then.
We don't have his video.
Okay, Dr. Shin, you are here? Dr. Shin? Dr. Eugene Shin?
Yeah, I'm here. Can you hear me?
Can you present it this time? Because Dr. Rao didn't provide.
No, I can, but can you run my video?
You did? Okay. Can you?
Yes, please.
Please.
What I'm presenting today is our latest developments in the newly invented MMEI system for high voltage applications. As a brief background, the electrified aircrafts could have obvious benefits as listed. A primary challenge, especially for large-size airplanes, was the high power demand, which typically requires larger currents and thus larger conductors, and that would result in huge weight and volume increase, even though heavy mechanical and pneumatic machineries would be removed. One solution to avoid the larger conductors for reasonable weight management was to use a high voltage, but then it would require much thicker insulation with any state-of-the-art system, again significant weight gain. On top of that, current high voltage cable technologies mostly developed for sea level were not suitable for the high altitude applications due to higher corona susceptibility. In addition, the system should also meet high frequency and high temperature requirements. Therefore, developing a lightweight but high voltage, high temperature, and corona resistant insulation system was critically needed. Since we started our first project a few years ago, we discovered that multi-layered structures of thin polymer insulation films significantly improved the dielectric strength if they were well bonded. As an example, for the same overall thickness, dielectric breakdown voltage VB of a 19-layer structure made of very thin layers of the Kapton and PFA was much higher than that of a 3-layer structure made of a bit thicker layers, which was yet still higher than that of the single-layer materials. Optical micrographs here confirm that heat fuse bonding with the PFA semicrystalline polymer provided excellent bonding integrity. This multi-layer structure was named as MMEI and fully patented in early 2020. The nomenclature illustrated below is the typical MMEI layup configuration convention used throughout this paper. Multifunctionality was another major thrust for this MMEI development, obviously for its structural concept and designability. Major functionalities needed for high-voltage insulation systems in the electrified aircraft applications are illustrated in the schematic drawing, but based on our experiences so far, they will require more extensive and systematic optimizations rather than simple addition. The initial candidates used for MMEI development were mostly commercial SOA insulation materials with good thermal stability, available at various thicknesses, including several different Kapton PI films with specific functionalities, a few semicrystalline polymers as bond layers, such as PFA, PET, PIC, and PTFE, also as moisture barrier, and mica film as a corona barrier. In addition, as a competitor, Surlex material, another multi-layer structure, but only made of Kapton PI, developed by Freylock using a proprietary adhesive-less lamination process, were tested. MMEI samples were fabricated by a simple compression molding for small dielectric test samples, or an autoclave process for large samples, as well as complex 3D structures and prototypes. Both were a batch process, but continuous processes are also being developed. VB was the primary property used for material screening and optimizations. We used the commercial system following the ASTM standard. The testing was done either in oils, typically with small size samples, or in air,
which is closer to the actual surface environment, but required much larger samples because of high voltage flashover. So pressure gasket fixture was designed based on ASTM suggestion. The test also measured the leakage current, a small pass-through current, even well before the breakdown, mainly due to imperfection of insulation material, thus relatable to partial discharge potentials. Now let's look at the test result. Figures here summarize the overall dielectric performance of the representative SOA materials as a function of sample thickness, either in oil or air, as a baseline for this study. In most cases, they follow the logarithmic trend lines. Even though the VB values varied with the material types, the most interesting finding was the opposite behavior in the delta VB to thickness relation between Kapton and other semicrystalline materials, as changing the test medium from oil to air. The former goes down while the latter goes up with increasing thickness. In any case, PFA, which was selected as the best bond layer so far, showed the least changes. The figure on the left is the master plot summarizing performance of MMEI structures to date in direct comparison with the SOA materials. Clearly, MMEI outperformed all of SOA materials regardless of test medium. The plot on the right shows the best performing MMEI configuration consisting of 1 mil thick HN and PFA, and its VB increases with increasing the repeat unit more than proportionally. To date, the highest increase was 91% from 17H4 sample compared to Kapton alone sample. As somewhat expected for its laminated structure, the Surlex samples also performed quite well, but as a bit of surprise, laminates of other semicrystalline polymers performed very poorly, which suggesting different mechanisms. Another strength of MMEI structures was the low VB drop in air, less than Surlex or Kapton materials. As I mentioned earlier, we also monitored the leakage current. Overall, the SOA single-layer materials showed the lowest LC either in oil or air. Then MMEI next, much lower than that of Surlex, particularly in air. In addition, as a proof of the concept, LC of PFA increased considerably after exposure to 350 degrees C, but no changes for the Kapton PI, which had much better thermal stability. The data I presented so far were from 60 Hz AC, but with DC, VB was much higher in all material types, but MMEI showed the greatest increases than any other materials, including Surlex. Besides, under DC, the Kapton material showed no pre-failure damages, such as microcracks, unlike under AC, and this might be related with the lesser increase in VB than PFA. We've been also investigating partial discharge behavior of MMEI structures in collaboration with Ohio State University team. We do not have any substantial result yet, but more extensive and systematic testing is underway. I just wanted to recognize the importance of this for MMEI development. Now let's switch gears and talk about mechanisms. Earlier on, with the significant improvement of VB with MMEI structures, we speculated some responsible mechanisms as listed. While they were convincing, we still wanted to validate them using the below three approaches, but I'll only talk about the 3D failure analysis today. The analysis was done relatively easier with the RoboMet, the automatic serial polishing and micrographing system. Initially, we started with 9 representative samples as shown in the pictures. They were mounted into one RoboMet sample to save time and efforts. All samples were aligned by the coordinate system, and the distance between each cross-sections were monitored accurately for the overall dimension dimensions. This slide shows a sequence of representative cross-sections from the 17H4 sample failed in air. As marked in the micrographs, you can easily find where the voltage broke in, propagated, and out. The complete damage and failure modes are listed in red, and their dimensions were also calculated. More importantly, it seemed that the local voltage was intensified at the interlayer interfaces and released through repetitive sequence of interface debonding and propagation, followed by through-layer perforation process, resulting in lengthier, more tortuous failure paths. Thus, one of the potential mechanisms was confirmed. A similar path was also observed from 17X sample. This is the sequence of the same 17H4 sample, but failed in oil. They looked slightly different, but basically progressed by the same lengthier and more tortuous failure path. And note that the overall damage zone was much larger than that failed in air. And again, the 17X sample showed a similar failure path. However,
So we have stopped here because we don't have much time.
Thank you, Dr. Shin. Next paper will be abstract number 545 from Daimler University and Helwan University and Al Shama University from Cairo, Egypt. Dr.
Yes,
Abu
we are here.
and Majid will be present.
Yes, we are
Please
here.
do.
Thank you very much. It's now 2:30 a.m. Friday morning in Egypt. I will share my screen. Okay, I'll share now my screen. A presentation to AAA FM 2021 conference at UCLA. The topic, elastic magnetothermal and magnetocaloric effect of yttrium iron-free and holmium iron-free compounds. I am Mohammed Saeed, a member of the Department of Physics, Higher Institute of Engineering, Shur Academy, along with my colleagues and teachers from Dimyata University, Helwan University, and Ain Shams University. The outline of our topic: introduction, aim of work, basic equations, results, and conclusion. Introduction. The magnetocaloric effect MCE is defined as the heating or cooling, i.e. temperature change, of magnetic material due to the application of a magnetic field. Nowadays, there is a great deal of interest in using the magnetocaloric effect as an alternative technology for refrigeration. The magnetic refrigerations offers the prospect of the energy efficient and environmental friendly. Aim of work: calculating elastic properties of yttrium iron-free using first principle calculation Vin2K electronic code as implemented in Vin2K electronic code. Calculating magnetothermal and magnetocaloric properties of the two systems, yttrium iron-free and holmium iron-free, using the mean field analysis and standard relation for the total heat capacity. Finally, we will discuss the results of our calculation in the light of available experimental data to show the validity of the calculation methods we used. Basic equation of magnetization. According to the mean field theory, based on the two sublattice model, the total magnetic moment is given by this equation, where we add the magnetic moment from the rare earth sublattice to 3 of the magnetic effect of the iron sublattice. Both depend on the Perlin function as given by these two equations. The basic equation of heat capacity. The total heat capacity is 3 terms: the electronic component term, the lattice component term, and the magnetic component. The electronic component is given by this equation, for which the density at Fermi level energy is needed. We obtain it from the Vin2K code. The lattice component is given by this equation, which depends on the Debye temperature that we can obtain from this equation in terms of the mean velocity of wave. The mean velocity of wave, we can get it in terms of the longitudinal and transverse speed of wave, which in terms can be calculated by the bulk and the shear modulus obtained from IR-elast code implemented in Vin2K. Finally, the magnetic moment can be calculated from the mean field theory. The basic equation of magnetocaloric effect. The magnetocaloric effect consists of two processes: the isothermal process followed by an adiabatic process. The isothermal process can be calculated by disintegration, while the adiabatic process can be calculated by disintegration. Both integration can be done by mathematical code. The results. First, the results of density of states. Here, we calculated the electronic density of states of both holmium iron 3 and yttrium iron 3 to get the density of states at Fermi level that we need in our calculation. The results of magnetization. The temperature dependence in zero field of the magnetization of the holmium and iron sublattice and the total magnetization of holmium iron 3 ferromagnetic behavior is evident with compensation temperature of 395 Kelvin. The temperature dependence in zero field of the total magnetization of yttrium iron 3 show a ferromagnetic behavior is evident. The results of heat capacity. The temperature dependence of the magnetic specific heat of holmium iron 3 in different field show that the heat capacity reduces as we increase the external magnetic field. The temperature dependence of the magnetic specific heat of yttrium iron 3 in different fields. The field dependence close to Tc is indication of second order phase transition. The results of entropy. The magnetic entropy of yttrium iron 3, a decrease in magnetic entropy is found with increasing the magnetic field. The magnetic entropy of holmium iron 3, a decrease in magnetic entropy is found with increasing the magnetic field, as shown in figure. The results of elastic moduli. The results of yttrium iron 3 elastic properties as calculated from IR elast. We calculate the elastic constant from which we can calculate bulk modulus, Cher modulus, Young modulus, and Poisson coefficient. This in terms used to calculate the average wave velocity and the dipole temperature for this system. The results of a change in entropy. The isothermal change in entropy calculated by trapezoidal method for holmium iron 3 at different field, both direct and inverse Magneto-Caloric effect is shown. The isothermal change in entropy calculated by trapezoidal method for yttrium iron 3 at different field, only a direct magnetocaloric effect is shown. The results of adiabatic change in temperature. The dependence of T over C on temperature at different fields for holmium iron 3 show weak field dependence is shown. Similar behavior is found for yttrium iron 3 system. This weak field dependence justify using the following equation to calculate the adiabatic change in temperature. Conclusion. The bulk, Cher moduli, and the electronic density of states are calculated using the Venn2K ab initio electronic code. The pi temperature of yttrium iron 3 and holmium iron 3 are 500.5 Kelvin and 357.85 Kelvin respectively. The total magnetization for yttrium iron 3 and holmium iron 3 at 0 Kelvin is 4.8 μp per formula unit and 4.4 μp per formula unit respectively, in fair agreement with available theoretical and experimental values. Ferromagnetic and ferromagnetic behaviors are found in holmium iron 3 and yttrium iron 3 respectively. Direct magnetocaloric effect and both direct and inverse magnetocaloric effect are found in yttrium iron 3 and holmium iron 3 respectively. Finally, the temperature and field dependence of magnetization, the magnetic heat capacity, the magnetocaloric effect quantities are all indicative of second order phase transition in these systems. Thank you for your attention.
Thank you, Dr. El-Majid. Next paper is abstract number 645 from Lund University, Sweden. Speaker will be Namsen Please do.
Yeah, hello, I'm here, but can we have the video played? I think you have the video. Yeah, great. Thank you.
Hello, my name is Namsun, and I'm a postdoc from Lund University in Sweden. My talk is about the general trends of bimetallic nanoparticle structures that we investigated using molecular dynamics. Bimetallic nanoparticles are interesting because we have more degrees of freedom in changing the shape or size or structure for optimizing their properties. The motivation of this work was that we wanted to find the equilibrium structures of bimetallic nanoparticles, whether a certain combination forms a mixed structure or a coaxial structure or something else. And secondly, we wanted to find out why they form a certain structure. We basically wanted to know the rules so that we can predict the results. In order to answer these questions, we used molecular dynamics for 45 different bimetallic combinations composed of these 10 metals. As we were interested in the equilibrium structures, we started the MD simulations from bimetallic liquid drop at high enough temperatures and cooled it down to the room temperature. And to make sure it reaches the equilibrium state, we continued the simulations with Monte Carlo until they formed nice crystalline structures. And this is some of the simulation results. Now, if we look at, for example, palladium-silver combination, palladium is the one occupying the core, and silver segregates to the surface. Some combinations are mixed. Some look like core shell, and some are genus-like structures. At this point, we wanted to be more quantitative about these results instead of judging them by eyes. So to make a quantitative analysis, and because we were interested in the surface segregation level or coaxial preference, we used alpha-shape method to identify the surface atoms. Using this method, we were able to count the number of each type of atoms on the surface. That is, how many A atoms are on the surface, and likewise, how many of B atoms on the surface, and also for the core. And once we've done the analysis for the MD result of each combination, we made our own criteria to categorize the structures. For example, when neither of the material occupies more than 70% of the surface, we label them as a combination that prefer a mixed structure. On the other hand, if one of the materials occupies more than 90% of the surface, it is labeled as a high level of core shell structure. So based on these criteria, each combination was categorized as either mixed, low level of core shell, high level of core shell, or genus-like. So what we did is that we converted the MD results into a table that shows the equilibrium structure of each combination and which metal segregates on the surface or forms the shell. Now, if we look at aluminum here, when it is combined with other materials, it tends to form the shell or the surface. On the other hand, platinum tends to occupy the core when it is mixed with other metals. So once we have these results, we investigated further to find the hidden trend, the rules that determine the segregation level for a given combination. So essentially the question was, what makes a certain metal more core preferring and the other more surface preferring? There are some comprehensive work on this topic that inspired our work here. For example, global optimization technique was used to find the core shell preference. It showed that many different types of bimetallic structures are formed depending on the interaction energies. And there is also DFT studies where they found this sequence or the ordering of the metals that reflects how strongly a metal tends to occupy the core. But when we tabulated our MD results based on the sequence, the order of metals provided by their work, it didn't fit the MD results, our MD results nicely enough. So we wanted to find a sequence or rules that are hidden in our MD results here. In order to do that, we firstly looked up the possible factors, the features of element that are frequently mentioned as the governing factors in coaxial preference. For instance, cohesive energy, atomic radii, surface energy, electronegativity, enthalpy of mixing. We ended up considering a total of 8 different features, and for each combination, we wrote down the relative difference in each feature. And we wanted to see which factors are the deciding factors in determining the final structures that we see in the MD results. And the easiest way would be to visualize the whole thing to see the relationship between the features and the MD results. But as we have many features, it was hard to visualize it. So what we did was that we used some data dimension reduction method, such as the linear discriminant analysis, LDA. So using LDA, we could reduce the 8-feature dimension into 3 dimension, but with minimal loss of original information. So here is the results of such analysis. It can be done quite easily using Python package, by the way. So here, each data point represents each bimetallic combination, and also they are color-coded based on the equilibrium structure found by MD and Monte Carlo. We can see that the first axis explains the pattern quite well, because here on the left side of the axis, we see more of mixed structures, and as we move to the other side of the axis, we see more of highly segregated structures like high coaxial structures and genus-like structures. The method was quite good at separating the different types of structures, and if we look at this first axis and read what features are predominantly constituting this axis, we find that they are the cohesive energy difference and atomic radii difference. So essentially, the LDA analysis results shows that the deciding factors of the final structures we see in the MD results are the cohesive energy and atomic radii difference. The first general trend we see from the analysis agrees well with the previous studies that for a given combination, the material with larger cohesive energy and smaller atomic radius tends to occupy the core, and the other occupies the surface. And it was true for the majority of the combinations that we studied that the element with larger cohesive energy usually has the smaller atomic radius. And the larger the relative difference in both features, the higher the segregation level. And we could also see how much roughly the relative differences should be for a combination to form highly segregated structures. But there were combinations that deviate from that majority. That is, in some combinations, the element with higher cohesive energy has also large atomic radius. So in that case, the core preference of that metal decreases. This trend was seen, for example, some of the combinations of molybdenum, because it has unusually large atomic radius compared to its large cohesive energy. So we could update the old table by reordering this sequence based on each material's cohesive energy and atomic radius. For example, platinum is the most core preferring material among these metals we looked at, and this core preference of material decreases as we go up the table, and aluminum at the top is the most surface preferring material among these. The table is nicely sequenced because we can see by just looking at the color distribution that the highly segregated structures are formed at this corner, and the mixed ones are at the diagonal. So in summary, I talked about the molecular dynamics Monte Carlo simulations and analysis method that we use to find the equilibrium bimetallic nanoparticle structures, and how we used data dimension reduction technique to find the pattern in the simulation results, and some general trends that we drew from that analysis. Thank you very much for your attention.
Thank you, Dr. Am. Next paper is abstract number 19 from Donan Research Austria and Osaka University and AIST in Japan. Presenter is Dr. Barbara Stedlover. Dr. Stedlover, are you here? In front, do you have a recorded presentation?
Yes, we have their video.
Okay, can you upload?
Good afternoon. My name is Barbara Stadlober and I'm a principal investigator from UNM Research. I'd like to thank the organizers for this invitation, and this gives me the opportunity to talk about our latest developments in the context of ferroelectric and organic electronic devices on ultra-flexible substrates. Over the last decade, we have developed a technology based on ferroelectric polymers, which can be printed on versatile substrates like paper, foils, or leather. And we named this technology Pisoflex. The base material of Pisoflex is PVDF, a fluoropolymer that exhibits a spontaneous polarization of 185 millicoulomb per square meter in its unit cell according to ab initio calculations. The polarization arises from the net dipole moments between the hydrogen and fluorine atoms that are facing each other in the all-trans conformation, and this conformation forms the ferroelectric beta phase. In Pisoflex we use a copolymer of PVDF with trifluoroethylene, which, in contrast to pure PVDF, crystallizes directly from solution in the ferroelectric beta phase. And this is very important for printing, of course. The name Pisoflex illustrates the essential properties of our technology, namely pyroelectricity, piezoelectricity, and flexibility. Pyroelectricity, which is the sensitivity against temperature variations, is exploited in this example for proximity sensing. Then we have piezoelectricity, the sensitivity with respect to pressure and touch, whereby in this video a non-conductive touch interaction is demonstrated. We have then also mechanical flexibility that can be used, for instance, for the definition of novel bending gestures in a 3D input sensor, as it is shown here. And finally, also structure-borne sound and vibrations can be registered, which in this case the Pisoflex foil is adhered to the backside of a metal trim part and transforms it into a microphone. Because of its multifunctionality, Pisoflex can be used in many application fields like condition monitoring, smart city, smart mobility, and consumer electronics, just to name a few. But today, I would like to present an advancement of our technology towards medical devices. And we did that together with the Xrd lab from Osaka University. Common wearable medical devices have a lot of drawbacks. So, for example, 24-hour blood pressure monitoring systems are very bulky and thus uncomfortable to wear. This handicap often leads to stress situations during measurement and may also lead to interrupted sleep, resulting in biased or even false recording of vital parameters. So the demands for the next generation of wearable medical devices are obvious. Of course, they should deliver precise measurements, but in addition, they should be comfortable to wear and easy to integrate on the human body. Therefore, any bulky external power supplies and wiring should be avoided. Actually, what we need are self-powered sensor systems with wireless data transmission that are imperceptible for the user. For this purpose, we had the idea to integrate ferroelectric sensors on a just 1 micrometer thin Parylene substrate. Then the final thickness of the sensor film is only 2.5 micrometers, which is so thin that it is very compliant to the skin. The sensors are based on a solution-processed thin PVDF TRFE layer sandwiched between aluminum electrodes and fabricated via a foil-on-carrier technique. The ultra-flexible sensor foil can easily be detached from this carrier and later on attached to other substrates and, for instance, to 3D-shaped objects like the human skin. In this context, it is also important to mention that PVDF TRFE is a semi-crystalline polymer. After processing, the dipoles of the ferroelectric crystallites, here illustrated in green as green lamellas, are randomly oriented. Therefore, an electric poling field has to be applied in order to preferentially align the dipole moments and achieve a non-vanishing macroscopic polarization across the layer. Under opposing electric fields that are larger than the coercive field, which is about 50 volt per micrometer in the copolymer, the dipoles reverse their orientation repeatedly. And this is illustrated here as an axial rotation of the polymer chain. The chain rotation produces a Pauling current that peaks at the opposing coercive fields, shown in this graph in black. By integration of the area normalized Pauling current, we can get the displacement hysteresis loop, which is something like a fingerprint of the ferroelectric material. It shows the typically bistable nature of the ferroelectric polarization. And from this hysteresis curve, we can deduce the most important key performance indicator of the sensor, which is the remanent polarization, which is also the displacement at zero electric field. For the ultra-flexible sensor, the remanent polarization which we got was around 65 millicoulomb per square meter, which is a very good value. We have also performed a very careful investigation of the influence of thermal annealing of the ferroelectric layer. In Xrd measurements, we have observed an increase of the crystallinity for annealing temperatures in the range 70 to 130 degrees. 130 degrees is above the Curie temperature of 105 degrees, but below the melting point. The crystallinity in Xrd was parameterized roughly by the height of the 110 reflection peak. The increase in crystallinity comes with a proportional increase in the remanent polarization and also a decrease in the coercive field, and that can be seen clearly in the hysteresis loops. The change in crystallinity is also reflected in the morphology of the layer characterized by AFM. With higher annealing temperatures, the lamella-like crystallites grow in intensity and size, as you can see here. Then we investigated the sensor response under transversal loading by a stamp, where we see a clear difference whether the sensor is attached to a rigid support like glass, plotted on the left, or to an elastic support like rubber, plotted on the right. In both cases, the charge response curve correlates in shape and dynamics with the exciting force curve. But we observe a strong, more than 20 times increase in sensitivity for the same ultra-flexible sensor when attached to rubber instead of glass. And this behavior and increase in sensitivity was also confirmed by SEM simulations. Furthermore, the simulations also reveal that the sensitivity increases with decreasing Parylene substrate thickness. Interestingly, the simulated strain in the piezoelectric layer is largest near the edge of the stamp. Well, The ultra-small sensor thickness allowed us also to stack multiple sensors on one another and thus further multiply the sensor response. And we can do that also on a 3D shaped object like this pre-bent silicon rubber. So for 3 sensors stacked, we get a 3-fold increase in the charge response. Moreover, the superior sensor performance is also reflected in an ultra-fast dynamic response, where we have less than 20 milliseconds per Newton response time. And accordingly, the shapes of force excitation and charge response characteristics are nearly identical. The mechanical robustness of the ultraflexible sensors is also exceptional. The polarization hysteresis remains completely unchanged during bending around an 80 micrometer thin wire, as shown here on the left, and the sensor signal is also stable over more than 1,000 stretching cycles as plotted on the right. Let's now return to the starting point for this development. Here you see the ultraflexible ferroelectric sensors in a wireless e-health patch for monitoring the human pulse wave. The sensors were either mounted on the neck or on the wrist, and they felt nearly imperceptible. We could nicely monitor the pulse rate independent of the sensor area. So it was 54 to 63 pulses per minute for this specific subject. We could also extract an augmentation index from the ratio of the P2 and P1 peaks. The augmentation index correlates with the elasticity of the blood vessels. In this example, AI was about 56%. By using 2 sensors with a defined separation, we can measure the pulse wave velocity, from which it is possible to extract the blood pressure. In this example, it was about 130 millimeter mercury. This video here demonstrates wireless pulse wave measurements, whereby the
Sorry everyone, we have to stop here. All the PowerPoint and videos are available on our website.
Okay, all right, thank you. Next paper is abstract number 967 from Policia University, Peru, and Helmholtz, Gentrium, Berlin for Materials and Energy, Germany. Presenter is Dr. L. Please do.
Yes,
Dr.
please.
L.
Would you reproduce the video that I uploaded? Thank you.
Flexible.
Hello, my name is Paul Jontop. I'm currently a PhD student of physics at PUCP, and today I'm going to present the terbium doping and luminescent activation effects on the optical and luminescent properties of aluminum zinc oxide thin films. And this talk I will focus on the luminescent properties of this material. Aluminum zinc oxide is a degenerate semiconductor with a wide band gap. Due to this degeneracy, it shows a good conductivity while retaining an optical transparency. It's optical transparency. And it is also suggested as an alternative to ITO for different applications. What we wanted to do was to make it multifunctional by adding a new property, which is luminescence. It could be used in potential applications such as solar cells. For example, in this typical crystalline silicon solar cell, there is an energy downshifting or down conversion layer at the top to take advantage of this ultraviolet range of the solar spectrum. And our material could be used as that layer. So it also could be used in emitting devices and also in gas sensors. The samples were prepared by radiofrequency magnetron sputtering. This is a schematic of the system used with these deposition parameters. The substrate holder was rotating at this frequency to obtain a good homogeneity between the samples. The substrate holder was actively cooled during the deposition, and I would like to emphasize this based on previous work on our lab. with rarer doped wide bandgap semiconductors, we cool down the sample to induce a rearrangement of the terbium ion in this case and its surroundings to activate them by means of thermal treatments, thermal annealing treatments. So these thermal treatments were done in air atmosphere and in this temperature range. Both the as deposited and annealed samples showed good transparency. A similar approach was taken also for samples of terbium doped ITO. You can see it. You can see the results on this presentation, also in this conference. Okay, so here the figure on the left shows the normalized cathodoluminescence intensity versus the wavelength. Here is the spectrum for each annealing temperature, okay, for this sample with this terbium concentration. And as you can see, we obtained the characteristic emission for terbium. Okay. And to further analyze this, we took the spectrum area into three parts. So first the background emission, which covers the spectral range, the whole spectral range. The terbium related emission, which covers the peaks, just the peaks, and the excitonic emission, which is centered at 380 nanometers. And at 300 degrees of annealing temperature, we can see that the terbium related emission starts to increase until 500 degrees. So we believe in this range there is occurring an optical activation due to these thermal treatments. So there is an improvement of the terbium related emission. And if we increase the temperature up to 1000 degrees, the terbium related emission goes down to 0, while the excitonic emission strongly increases and is almost as equal as the background emission. So high temperature may improve the crystallinity, but may worsen the symmetry of the crystal field surrounding the terbium ions that is required to activate for the emission. So the consequence of this is this quenching. With this result, we believe that the energy transfer mechanism between the terbium ions and the host, the AC doped, is of excitonic nature. So in order to assess this possible energy transfer mechanism, we took the 400 degree sample to perform temperature dependent photoluminescence experiments. Here we can see the normalized photoluminescence spectrum related to the terbium emission for each sample temperature. So we took the logarithm of the integrated area, okay, and we plotted it against the reciprocal of the temperature, as you can see here in this figure. And we can notice that there are two regions where a quenching occurs. There's a decrease of the intensity. So both regions were fitted with an Arrhenius-like expression, like this one, and the lower temperature region was fitted with 2 energies, and the higher temperature with 1 activation energy. We interpret these activation energies as binding energies of excitons that are bound to terbium clusters. And we believe these excitons that are bound to these terbium clusters recombine, and their recombination energy is transferred to the cluster, inducing a photon emission from the terbium ions. So as we increase the temperature, there is a thermal dissociation of these excitons that induce this quenching. So we use 2 models for this kind of cluster traps, rare disovalent traps, and we use 2 models, the Koster-Slater model and the spherical potential well model. In the Koster-Slater model, we have 2 parameters to be calculated, the impurity potential and the host effective valence bandwidth. And these are the expressions to calculate the binding energies. In the case of the spherical potential well model, there is a potential depth, which is the same regardless of the number of ions inside the cluster, and the effective radius. So with this, we can calculate the binding energies corresponding to this model. These are the calculated parameters for this model, and although they are not in well agreement with the values that we could obtain from the literature, we could calculate the corresponding energies for the cluster with 3, 4, and 5 ions. And we obtained that as we increase the number of ions in the cluster, the binding energy increases. Okay, so the third experimentally obtained energy was around 800 millielectron volts, which could be related to a cluster with 8 ions. And we believe that for this terbium concentration, there is a very low probability for that cluster to form. So this energy, this high energy, binding energy, could be related, or activation energy, could be related to a different quenching process. Okay, anyway, so we took a sample with a slightly higher terbium concentration, and we also did the temperature dependent PL experiment, and we found this curve. So we used 4 activation energies to fit the data, and with the 2 lowest binding energies, activation energies, calculated the parameters for both models, and these results are in a well agreement with the values that we found in the literature. So with these parameters calculated, we further calculated also the corresponding binding energies for the cluster with 3, 4, and 5 ions. As you can see, those in green are the experimentally obtained binding energies, and those in blue and red are from the Koster-Slater and the spherical potential well model. Those with 3 and 4 ions in the cluster, we can see that the experimentally obtained values are in well agreement with the calculated ones with the model. Okay, to summarize this talk, we have seen that we obtained the terbium-related emission, the characteristic terbium-related emission, and for a temperature at around 300 degrees Celsius in thermal treatment, there starts an increase of the terbium-related emission. So we believe that there is an optical activation of these ions, so their intensity is increasing. And we took a sample with a slightly higher terbium concentration, and we found, by means of temperature-dependent PL experiments, that there could be 4 activation energies, and we relate these activation energies as binding energies of excitons that could be bound, that are bound to the terbium clusters. So we took 2 models for this interpretation and found the corresponding binding energies, and we found that for the cluster with 3 and 4 ions, the experimentally obtained binding energies and those calculated binding energies with both models are in well agreement. So also you can see here in this talk the terbium doped ITO results, which show a similar approach as the one presented here, and also the ITO results on the opto-electronic properties obtained by ellipsometry. And I will finally...
Thank you, Lanta. Next paper is an invited paper, paper number 679 from INRS from Canada. Dr. Pignonlit, will present.
Yeah, I'm sharing. Okay. This one. Okay. Good afternoon. Where is that? Yeah. I'm Alain Pignolet. I'm professor at INRS, the Institut National de la Recherche Scientifique in Montreal, Quebec, in Canada. I want to thank the organizer to have invited me to present the results of the research of the last years. And the title of my talk is A Quest for New Room Temperature Multiferric Thin Films. And the room temperature is very important, that you will see. So this work has been done by my former students Riyad Meshash, Luca Corbellini, and Tamer Hajlawi. My present student Caloric, who is continuing the work, Dr. Katarina Nadja, all at INRS, as well as Professor David Ménard and Dr. Christian Lacroix at École Polytechnique de Montréal. I acknowledge, of course, the people who have funded the research as well. So just a small reminder, what is a ferric material? A ferric material is a material which possess two stable domains, which are discriminated by an order, physical properties, usually a tensorial or a vectorial physical properties called an order parameter. The most known, the three order parameters are the magnetization, polarization, and strain. So the most known is probably the magnetization, the dielectric polarization, and the strain. And a ferric material has therefore a spontaneous magnetization even in the absence of magnetic field, spontaneous electric polarization in absence of an electric field, or a spontaneous deformation of spontaneous strain in absence of of mechanical stress. This stable domain, this property can be inverse. The order parameter can be switched by the mean of the conjugated field. The magnetic field switch the magnetization, the electric field the dielectric polarization, and the mechanical stress would switch the strain. And ferroics are therefore be characterized by the presence of domain and by the presence of a hysteresis loop when you sweep the conjugated field along from negative value to a positive value, and you switch the domain. So here all the domains are in this state, then you have here you have the remnant polarization or magnetization or strain at zero field, and then you go to the inverse and you come back. Of course, multiferroics by extension is very easy to understand. It's just a combination of two or more ferroic orders. For the purpose of this talk, and most commonly the current convention when we speak of multiferroic means ferroelectric, which have magnetic properties. So it's a magnetic ferroelectric, so which has both magnetic order, the polarization, and magnetization. This terminology has been extended also to composite or heterostructures such as multilayers. One interesting properties of the multiferroics is the coupling between those two orders, order parameters. So the coupling between polarization and magnetization. This coupling is called the Magneto-Electric coupling, which means that you could control or manipulate the magnetic field with an electric, the magnetization with an electric field, or vice versa, control the polarization with a magnetic field, which is actually what makes these materials most interesting for application. And there is quite a lot of promising application which have been already devised. I'm not going into detail here, I don't have the time, but one of the very interesting properties that could be used is to replace the current-driven magnetic writing head of a magnetic field by something which is just voltage-driven, because, as you know, current-driven devices have a lot of power consumption, so you can save a lot of power if you do something by using some voltage control and not current control. But of course, as you speak of application, you want this material to be multiferric at room temperature or above. And presently, most of the material which are multiferric are actually multiferric at pretty low temperature or extremely low temperature. Until very recently, bismuth ferrite was one of the only material which was known to be multiferric at room temperature. Then Spalding et al. Calculated in the computer that if you replace one of the iron by chromium, you have a material called BFCO, and this material would be multiferric. Actually, we have been able to do that in 2007, and that's what I will speak about. It's one of the material I will speak about today. Since then, some other material have been actually made which are multiferric at room temperature, but nevertheless, they are still very, very few compared to the number of ferroelectric or magnetic material that you have in nature and in application. So how can you do multiferric material? Well, you have several strategies. You can, in the material which are single phase, you can try to add, right, between quotes, to add magnetism to good ferroelectric properties. That's what has been done with BFCO. Or you can try to add some good ferroelectric properties to a good magnetic material, which is what I will speak with epsilon ferrite, with the epsilon phase of F8O3. Another strategy would be to use composite materials, where you have materials which are one material which is a good ferroelectric, another one which is a good magnetic material, and you put them together. But that's not what I will speak today. We don't have time. That's the subject of another talk. All the materials which I will present here today are actually thin films. Thin films, most of them actually epitaxial thin films, which have been done by Paisley position. Here are the parameters. But, you just have to remember it's thin films that I'm presenting here. So bismuth ferrite, BFCO, bismuth iron chromium oxide, epitaxial thin film synthesized by PLD. So as I said before, this material, BFO, bismuth ferrite, was one of the only one which was considered multiferric at room temperature until very recently. And Spalding, a co-worker, by doing simulation, predicted theoretically that if you replace one of these iron with a chromium, so now you have iron, chromium along the 1-1-1 direction, then this material, which is actually a pretty good ferroelectric, but a pretty lousy magnetic material with only 0.02 Bohr magneton per formula unit, could actually become much better, magnetically speaking. Like you see, it could become a material with a 2 Bohr magneton per formula unit on also very good properties. The only thing is that in order to do that, you have to have a cationic ordering. You have to have, along all the direction, you have to have an ordering of chromium and iron and chromium and iron. And people didn't really know how this would happen. And if it would happen, it has been controversial for a long time, until actually we decided just to try. And we did find some conditions in which this ordering, this cationic ordering, is actually happening. So this is actually the experimental part. Okay, so we have actually still here the structure, which is a double perovskite. With this unit is not the same as this unit. So the unit cell is composed of 2 cubes, and you have here the ferroelectric loop and the ferromagnetic loop. You see that in the thin film form, the ferroelectric loop is a little bit leaky. At low temperature, it's much better, and that the magnetic properties are actually pretty good. And they are indeed almost 1.9 more 1.9 more Bohr magneton per formula unit at room temperature, which is almost the 2 μb per formula unit predicted theoretically. So we were very, very happy about that. As you can see, you really have a cationic ordering. You can see here the Xrd spectra, where you see the 2 superlattice peaks. You see the same thing in the electronic diffraction pattern, where you have the superlattice spots. And so you do have, even in experimentally, you do have certain cationic ordering happening. And we believe this is happening actually because the strong repulsion between the iron-iron cation would be actually decreased drastically if you put a chromium atom in between. So this is actually what creates the ordering. This is a phase diagram, so of course we have some very narrow window in which things are working in the blue region, and of course depending on the exact synthesis condition, you have a different cation ordering on this, as you can see here as well. And this cation ordering is also actually depending on the thickness. As the film grows thicker, cationic ordering is decreasing. So that was for the BFCO film. As I said, we believe that the chromium is shielding the strong interaction between the iron-iron, and that's what is creating the ordering. The other material I want to speak about is epsilon ferrite, and this is a potentially multiferric material, which will be, of course, very, very interesting because it's only iron and oxygen, non-toxic, abundant, and very well known, but it's the metastable epsilon phase. This material is actually an intermediate between the alpha phase, which is the hematite, and the maghemite, which is the gamma phase. And it's stable only in a very, very small region. And that's why we have, up to very recently, only nanoparticles of the epsilon ferrite, the epsilon phase of Fe2O3. Very recently, this material was also interesting because it has, well, it is the highest oxide, is the highest magnetic anisotropy on a huge coercive field of 20 kilohertz, which has the consequences that it has a ferromagnetic resonance frequency in the low terahertz range, which is also something interesting for application. It has, epsilon ferrite has a pretty complex crystal structure. You see, you also have the oxygen octahedra, that you have an oxygen tetrahedra here, and you have an antiferromagnetic coupling, but because this one is smaller, that's the ferrimagnetic, you have a net magnetic moment upwards in this case. Because of the orthorhombic crystal structure on the group, the space group PNA21, this group is a polar group, so this material is at least pyroelectric and potentially ferroelectric as well. So what about epitaxial thin films? So epitaxial thin films on perovskite, 111 oriented perovskite substrate, which shows 3 different substrates here in order to modulate, to change the strain, the epitaxial strain, give a very complex epitaxial relationship, which looks like this. You see the substrate, the 111 plane of the substrate behind, and you see the perovskite. So you see the epsilon ferrite on top, and this is on 111 oriented perovskite substrate, or in 100YZ, you have even more complicated epitaxial relationship, which you can see here. And these epitaxial relationship have been found by actually providing the best continuity of the oxygen sublattice between the crystal and between epsilon ferrite and the substrate. Why is it interesting to have it on YZ100? Because YZ100 can be very easily grown on silicon. Therefore, those materials, those thin films, potentially multiferric, could be grown on a silicon, with a silicon compatible technology. As you can see, they are epitaxial. So along the C-axis, they are perfectly epitaxial. But along the in-plane, of course, you have this very complex epitaxial relationship. Well, that's a magnetic field, that's a magnetic curve, and the magnetic coercive field is actually not exactly as large. You remember it was 20 kilohertz. That for a nanoparticle, it's a little less, because for magnetic nanoparticle, you have a single domain. You have this pinch loop, which can be very well explained by a very, very small amount of magnetite within the Fa2O3. But as I said, because of this very complex epitaxial relationship, this material, which was strongly anisotropic, is now having a lot of twin, and the anisotropic properties are actually becoming pretty isotropic, which is not good. So what we did, is we try to use miscut substrate. You see here the substrate, the miscut angle is increasing. And by doing that, you can select one of these orientation. And indeed, the magnetic properties now are again oriented along only one direction, as you can see here. So in summary, that you have here two single-phase thin films, epitaxial thin films, which are ferroelectric and magnetic. And remember that when you want to do some application, you want the material to have the property you are looking for at room temperature. And the room temperature, even in Canada or in the north, is not the liquid nitrogen or liquid helium temperature. Thank you for your attention.
Thank you, Ignolet. Next paper will be last paper in this session. Abstract number 826 from National Chongqing University. Speaker is Professor Cheng Chung Chung. Dr. Chung?
If Dr. Chung is here, we can play his video.
He has recorded the presentation slide?
Oh, yeah, he has a video.
Please upload.
Thank you for the opportunity to join AAA-FM conference in UCLA 2021. We are glad to introduce our study. Three-dimensional plasmon generating nanostructure for surface-enhanced Raman scattering and plasmon-enhanced fluorescence detection. Introducing myself, I'm a postdoc in the Intelligent Minimally Invasive Device Center of National Chongqing University in Taiwan. As known, Raman spectroscopy provides detailed information on molecular fingerprints, even though the Raman scatter intensity is very weak. Here we prepare silver nanowire to manipulate surface plasmons, resulting in enhanced Raman scatter intensity. And the localized surface plasmons enhance the electromagnetic field around the nanostructures. For plasmon-enhanced fluorescence study, we utilize these properties of nanowires to detect some selected organic molecules, such as pesticides. At first, we synthesize silver nanowire by wet chemical approach, and the dynamic light scattering analysis show the average diameter of nanowire to be about 115 nanometer and length to be 15 micrometer. Our synthesized nanowires show a broad absorption spectrum spanning over the entire visible region. So the broad absorption nature of our nanowire is suitable for PEF application. We sprinkle specific amount of a synthesized nanowire onto a glass slide and let it dry. And the sprinkle and dry steps will repeat until wood-pile packing was formed, thus creating a three-dimensional random cross-wire wood-pile nanostructure. The wood-pile nanostructure can have many 3D hotspots, which can enhance Raman scatter signaling from the probe molecules. And with the analysis on this 3D RCW platform, we proceed to search and PF analysis. We also characterized the 3D RCW nanostructure using the optical microscopy, AFM, and SEM. The wood-pile nanostructure have many intersection points for hotspot generation in this trip. To evaluate the performance of the 3D RCW chip, a common standard chemical, rhodamine 6G, was used to test its Raman signal in different density of nanowire in the chip. An optimized nanowire amount hereby results in enhanced surge response from R6G. Surge measurements were performed on 7 different positions and averaged. The spectrum from 7 positions were consistent as shown. The stable nature of the platform is also evident from the figure, where the surge measurement will perform after 18 days. Furthermore, we can detect R6G with molar concentration close to the picomolar level. We also check the PF R6G in our 3D RCW chip. For instance, from R6G present on the platform is observed to increase with the increase of nanowire amount. Importantly, R6G, for instance, was 1004 compared to that of the V R6G in the solid state. From the PF analysis, we also observe a high degree of fluorescence at the intersection point and at the end point of the nanowires. The shorter and small concentration of nanowire present bright spots at both ends. Therefore, longer nanowire with more intersection size prove to be responsible for both surge and the PF effect. Finally, we test the 3D RCW chip to detect some selective participants such as cyanide, perchlorate, carbide, and fipronil. Compared to the normal spectrum, significant surge enhanced signals from the participants was observed. For example, the major CN stretching peak from cyanide show higher surge intensity in comparison to the normal scatter intensity. We also investigate the limit of detection from this participants on our 3D RCW chip, which are shown in the insert. We further studied the PF effect from this participants in the 3D RCW chip by fluorescence microscopy. The carbide, perchlorate, fipronil present blue, cyan, and green fluorescence in our chip, respectively. The PF result complemented well to the acquired fluorescence spectrum. In this study, we developed a 3D RCW chip, both taking surge and PF effect for detections into account. This chip is stable and provides excellent limiter of detection in R6G. The wood-pile nanostructure present in the 3D RCW chip provide as many plasmonic hotspots, thus leading to higher surge and PF response from the probe molecules. And this 3D RCW chip thus proved to be utilized in pesticide detection. Thank you for your attention.
Thank you, Dr. Cheng. This is the last presentation of this session. Here is my closing remarks. Number one, I apologize for some trouble in presentation order because I have all the version of presentation schedule. That was trouble. I really apologize that. Number two, we appreciate the two invited speakers, Dr. Borger and Dr. Pignolet, and speakers, and also participants. And number three, let us keep in touch to meet at AAFM UCLA 2022 next year. We hope to meet face-to-face at that conference, hopefully. And lastly, EPMM-4 session is now closed. Therefore, I want to say this. Good morning in some country. Good afternoon in some country. Lastly, good night. So long. Thank you, all of you. Bye-bye.
Thank you.
Thank you,
all.
Professor.
Thank you, guys.
Thank you, Professor.
Don't forget next year UCLA conference.
Thank you.
We hope to meet there physically.
We hope so. We hope so.
Thank you, sir.
All right. Thank you for organizers too.
Thank
Bye-bye.
you for Palembang, Indonesia.
Thank you, Doctor. Thank you, Dr.
Thank you,
Hong.
everyone.
Indonesia.
So
Yeah,
long.
thank you. Thank you.
Jingguan,
Thank you.
Yeah, I'm here.
can you please play the video for Dr. Ramchandran, which we missed
Thank you so
in
much.
our discussion?
Thank you, Jinsha. I appreciate you. We had the trouble with my old schedule. Okay,
Thank you for your hosting.
Okay, you did a good job for us. Hopefully to see you next year.
Yeah, I will still stay here. And
if you stay, if you stay
yeah.
next year, we will see there. Okay, bye-bye. Bye.
Bye, Professor. But we still have one video from Professor Rowe. I think if
you have that? You have that?
Yeah, if everyone
okay,
want to
can you upload? Hey, gentlemen, we have one more recorded presentation. Can you stay with us, please?
Yeah, I prefer.
Okay, sir, we will stay. Okay.
Okay, please stay.
Hi, this is
Thank you, all of you.
Presentation. The title is Making Diamond an N-type material with enhanced conductivity via ion implantation technique. I belong to the physics department of IIT Madras and the Quantum Center and also the Nanofunctional Materials Technology Center. As you know, diamond is a very fascinating material with a plethora of very interesting properties. It has a very large band gap of 5.5 electron volts. It's an insulator, but it can tune its conductivity by doping. Boron doping makes it a p-type semiconducting system, and with higher concentrations of boron doping, you can even realize superconductivity. It has very high thermal conductivity. Thermal conductivity of diamond is 4 times more than that of copper, high electron and hole mobilities. And you can envisage a plethora of applications with diamond electronic devices, high frequency field effect transistors, PN junction diodes. And today it's all about using NV centers in diamond for fabricating room temperature qubits, quantum bits. The drawbacks are large carrier activation energy of doping. So in our group, we have established diamond growth process. We can make a microcrystalline, nanocrystalline, and ultra nanocrystalline diamond coatings, thin layers, even thick layers, and for some measurements like specific heat. And at high doping concentrations of boron, you find superconductivity in diamond, and with superconducting transition temperature anywhere from 2 to 6 Kelvin. And the superconducting transition is very robust, and it doesn't vanish even at 4 Tesla of external magnetic field. The challenge, of course, is making it a N-type material, because as you can see here, the donor levels are deep inside the forbidden gap. The nitrogen donor level sits 1.7 electron volts below the conduction band. Nitrogen and phosphorus make good substitutional impurities. Lithium and sodium go into interstitial sites. There are three ways in which impurities can be incorporated into diamond lattice. One during the growth process, CVD growth process itself. Second, by indiffusion. It depends only on solubility limits. And the third important one, which is useful in the case of nitrogen and phosphorus doping, is the process of implantation. But there are lots of challenges there. What is the challenge here? When you start with nanocrystalline and ultra nanocrystalline diamond, when you implant it, most of the implanted ions tend to diffuse towards the grain boundaries, and with further annealing, they in turn diffuse into the grain. So unless you have the carbon atom being replaced by nitrogen and phosphorus, leading to an electron being donated to the lattice, you will not see conductivity enhancement. So the advantages of nitrogen implantation is precise control over the number of implanted atoms of the dopants. So you can precisely control, then you can tune the conduction inside the lattice. The disadvantage, of course, is amorphization of the lattice due to high ion impact, and which can be solved, of course, by the process of annealing. So that's what we have adopted in this study. We have grown extremely good quality ultra nanocrystalline diamond films, and then bombarded them, implanted them with nitrogen and phosphorus ions, and you can see the systematic change in the microstructure from the undoped one and higher doped or implanted nitrogen ions from 10⁻⁵ to 10⁻⁷ ions per centimeter square. Yeah. So the vibrational properties of nitrogen implanted ultra nanocrystalline diamond, the summary of this slide is that the implantation causes an increase in sp2 content especially in the damaged regions, and it causes an increase in sp2 bonding and ordering in grain boundaries, which leads to a shift in the G peak position. Now, if you look at the grazing angle X-ray diffraction, this study has given us some interesting results compared to the undoped undoped ultra nanocrystalline diamond. The implanted one shows an additional peak, 110. And then when the grazing incidence increases from 3 degrees to 10 degrees, by which process you're increasing the penetration depth of X-rays into the matrix, you'll see the intensity of this peak increasing, right? Which shows the effect of implantation clearly by the X-ray diffraction process. And these films are highly crystalline, and this is a beautiful high resolution transmission electron microscope image where you see the hexagonal arrangement of the diamond atoms, and depth resolved X-ray photoelectron spectroscopy measurement clearly shows the presence of phosphorus and also nitrogen in this case, inside from the top into your depth of about 300 nanometers, which is a clear indication of the presence of phosphorus as well as nitrogen in the diamond film. We have been able to see an enhanced conductivity with nitrogen and phosphorus doping. The low fluence gives rise to an insulating behavior, high fluence gives rise to a metallic behavior, and such high conductivities have not been seen so far in the implanted diamond films, either with nitrogen or phosphorus. So we have fitted the resistivity data with the standard MOTS variable range hopping mechanism. The electron mobility values obtained in the medium fluence regime are about 0.2 centimeter square per volt per second. When you come to the films, implanted with higher fluence, we use the quantum corrections to conductivity model, the QCC model, to explain the process of conductivity, which with a nice fitting of the entire data from room temperature down to the lowest possible measured temperature using the QCC model. And what we conclude is the conduction is like a Fermi glass type conduction often observed in heavily doped compensated semiconductors or amorphous semiconductors. A quick look at the X-ray absorption spectroscopy of implanted UNCD shows that you have the C1s exotonic peak diminishes, and then the higher doping or implanted regimes, you see no signature of crystalline graphite. So low point defects, moderate disorder to high TAC content as you move from the low to high implantation regimes. Coming to phosphorus implantation, we see a similar result as in the case of nitrogen. The conductivities are significantly enhanced, but the highest conductivity is seen for 5 into 10 raised to 16 ions per centimeter square itself. But in the case of nitrogen, you have to go 1 order more of implantation fluence in order to realize the highest conductivity. And we could explain the conduction process, even in this case, similar to what we have in the case of nitrogen implanted UNCD films. A linear Hall effect reveals the signature of two-band conduction mechanism, one via the impurity band and the other through the conduction band process. So in summary, what we are seeing is in ion implantation, the grain boundary transport or grain boundary doping phenomenon does not fully explain the transport properties. We are actually looking into our recently carried out atom probe tomography data to understand more at what's happening at the atomic level. A sp3 rich tetrahedral amorphous carbon signature is evident when implanted at very high fluences. In phosphorus doping, a semi-metal-like conduction is seen, which is an evidence of band conductivity with strong enhancement in mobility of lower electrons, point towards the fact that we cannot completely rule out the possibility of phosphorus being substitutionally doped in diamond grains. So our atom probe tomography results would clearly reveal that aspect of what's exactly happening at the atomic level when nitrogen and phosphorus are doped. So thank you very much for your...
Thank you, Professor Rao. Jinghua, do you have a second paper for him?
A second paper?
Yeah, recorded the presentation slide for his second paper. Do you have it?
Let me see.
Oh, Dr. Hong, excuse me. No, Dr. Hong, we don't have a second paper for him. So this is the end of session for EPMM. Thanks to you for your services, for chairing this session.
Abstract number 1631. Jingfar?
Hi.
Abstract number 1631 from Professor Rao. Do you have a recorded presentation slide?
We don't have. We have played.
Oh, you don't have, just only one you have.
Yes, we just have this.
Okay. All right. Once again, everyone, thank you so much for your participation. Looking forward to seeing you next year, AAFM UCLA conference. Bye-bye.
Bye-bye. Thank you for
Bye-bye, Doctor. Thank you.
Thank you, Doctor. Bye-bye.
Hi. Today is all our work is done.
Yes, we are done for today. Thank you, Jin Yon. You have done a great job today.
Welcome. See you tomorrow. Bye-bye.
Yeah. So tomorrow we have a last day. And tomorrow we will finish early.
Bye-bye.
Bye-bye. Thank you.